Okay. All right. So I shall talk about string theory. Sorry, string theory and its role in 21st century mathematics. Okay. I understand that most of you are physics undergrad, so some of these concepts could be familiar to you, but I will give you a sort of a comprehensive introduction into this field. Okay, so the end result of today's lecture, or rather talk, would be that you have some general idea of string theory, and you can therefore know where to look for the resources to study more about it. Okay, so that's the whole point, to give you a pedestrian introduction into this thing, and to also illustrate the beauty of string theory and its impact on cutting-edge mathematics. Okay, so let's see what we'll do today. So the outline of the talk will be, of course, I will just briefly go through the important physical theories that we have discovered before the 1980s. Why the 1980s? Because 1980s is the time when string theory was in some sense discovered. I mean, strictly speaking, it was discovered by accident in the late 60s and the 70s when people were trying to study something else. Okay, they were trying to study hadronic physics, which is the physics of the strong interaction, things that are involving the nucleus. And so they couldn't solve certain things, and then they said, someone came out with the idea and say, why not we imagine that we don't have point particles, but we have extended objects? So they postulated that in the 60s and 70s, okay, late 60s and early 70s, and to try to solve that problem. But in the end, they couldn't solve that problem, but they discovered that if you postulate something not to be a point particle but an extended string, you could bring gravity into the equation, at the quantum level. And that was the birth of string theory. Okay, they abandoned using that string theory for that purpose, but then they came up with the idea of, the theory of everything using strings. Okay, so that resulted in the full force, development, or rather effort to develop string theory in the 1980s. So I think it's essential that before we talk about string theory, we talk about the physical theories before the 1950s. Okay, because physics, as you understand, is a foundational subject. So if you want to know something, say, in say thermodynamics, and you want to understand, for example, kinetic theory of gases, then you first know classical mechanics and all those things, right? So likewise, it's the same thing. String theory builds on theories, its concepts built on theories that came before it. Okay, essentially quantum mechanics and relativity. Okay, so we'll discuss that. And then I will go on to tell you why we need a unified theory in physics. Some of you may ask, why would we need a unified theory in physics? I mean, we have all the theories that we need that will describe the world. Let's say you want to describe the stars, the cosmos, black holes, and the fate of the universe, cosmology. We have general relativity, which is the theory of gravity and space and time, and our most updated theory of mechanics. Okay, so this is something which people don't emphasize enough. Einstein's theory of relativity, the general theory, is actually our most updated, theory of mechanics with acceleration. Okay, so, and why gravity comes in? Because of the equivalence principle between acceleration and gravity. And so, and studying a mechanical theory with acceleration, you also bring in gravity. Okay, so that's the reason. And so that describes for you all the big things. And then we have what we call the standard model, which we will go through also. That's the quantum field theory of things which are very small. The atom is actually the atom which makes up everything. So we have these two theories that can describe all that we need. So why then do we need a unified theory that describes this relativity theory and standard model together as one? Okay, so we will come to that, why we need to have a unified theory in physics. Okay, and then we start to introduce string theory, okay, as the theory that will help to unify, our best theory that would help unify physics, okay, the small and the big. We will show you the problems that we encounter in trying to unify it, and then we'll show you how string theory can actually solve these problems elegantly, and therefore we introduce string theory in this manner. So once we introduce string theory, then we can recast our understanding of what we knew about the universe in terms of string theory also. There are some models that string theory suggests of the universe that we have never seen before in the past, and these are very interesting. So this is in a field called string cosmology. Okay, string theory in the universe is actually called string cosmology, and that I think usually interests the general public the most. Okay, because so that's something which people can relate to, right? If anyone, you don't even need to be a scientist. You could be even a religious person, and people will ask, where did we come from, where will we go, what will happen after we die, and all those things, that's in the realm of cosmology. And string theory offers some scientific answers to some of these questions and maybe metaphysical ideas, to some of these questions. And then we will go through this under string theory and universe. And then to, of course, come to this part, which I think is very important, okay, I would say this is the most concrete contribution to string theory to date, okay, because right now, even though string theory has very nice, elegant ideas, because it is, a string is very, very small, it requires a lot of energy to prove in experiments to verify that it is correct. So right now, technologically, we are not there yet to generate such high energies to actually see a string. So as beautiful and as elegant as it is still not verified experimentally. So, but what we can say that, string theory has done concretely and irrefutably is its influence on 21st century mathematics. Okay, when I say influence, I mean even spawning new ideas in mathematics, much in the same way that Newton, in trying to study the mechanics of motion, right, the physics of motion, things rolling down the slope, how it falls under gravity, he had to formulate calculus, right, dy dx, okay, and integration. Work done is actually, force displacement graph, and then you integrate the area underneath, right? So those things, calculus, the mathematics of calculus, was born of Newton's desire to understand mechanics, right? And string theory is now doing the same kind of thing. There's a revival of this sort of feeding from physics into mathematics. Since Newton, there was a gap. After Newton, mathematicians went off on their own tangent and went to dizzying levels of abstraction on their own, okay, doing their own things in algebraic geometry and all that, which are sort of divorced from physics, right? All physics needed until even right up to maybe relativity was just calculus, okay? And even for relativity, if you look at GR, for example, right? GR uses off-the-shelf mathematics, Riemannian geometry to encode its ideas. So Riemannian geometry came about maybe, I would say, 50 years before Einstein discovered or formulated GR, which was in 1915. Okay, and that was Riemann lived in the late 1800s, so it was a few decades before. Okay, and then even if you look at quantum mechanics, which makes use of linear algebra and Hilbert spaces, that was 20 or 30 years. The mathematics of Hilbert spaces came about 20, 30 years before quantum mechanics was formulated. So you could see that all the theories we had, were using mathematics that preceded them. Okay, and then slowly in the later parts of the 20th century, in the mid-50s to 70s, physics went ahead and started, suggesting structures, in mathematics that have never been encountered before. Okay, and string theory was the, the sort of the leading theory that gave rise to a lot of this new mathematics. Okay, so we are in some sense seeing a revival, a 400-year later revival of this feeding of physics into mathematics. Okay, so you could see that we are again doing what Newton did, but through string theory. And this is the part which I work on and which I have much to say about, okay, and to show you. And then we'll conclude. Okay, the conclusion is also interesting in that there is a new notion of how space-time came about. I will talk about that in a while. Okay, and that's also a very fundamental topic. Okay, so physics before the 1980s. Right, so we had Newton's theory of gravity, 1687. Okay, I won't cover all the theories. There's also thermodynamics and all sorts of things, fluid mechanics, thermodynamics. Okay, but the crucial ones, right? So Newton's theory of gravity, 1687. So this is probably the only, okay, it's not the only equation you will see. It's the only equation you'll see up to the part where you'll talk about the 21st century mathematics. Okay, this is the only one. GMMOR squared. Okay, so Newton, his theory of gravity tells you that if you have two masses, m and small m big M, okay, they attract each other instantaneously. No matter how far they are separated, the action of attraction is instantaneous. Okay, so that was Newton's theory of gravity. And that it was only attractive, gravity was only attractive, okay, and that as you go closer and closer, the distance between each other, which is r, if the denominator gets smaller and smaller, then the force of attraction gets bigger and bigger. Okay, but the key point is that it acts instantaneously. Okay, that was 1687. Where there was no notion of the limit of speed of light yet. Okay, so 1687, fast forward to 1905. So then it was discovered around this time, firstly through Maxwell's equations, which was a theoretical thing, okay. Then later on, two engineers measured the speed of light, Michelson and Morley. Okay, they use like this wheel of mirrors, the very, very clever way of measuring the speed of light. So there's a peculiar thing about light. Firstly, light has a finite speed. This could have been seen from Maxwell's equations. Okay, 1 over square root mu epsilon, which appears in equations. And one more thing is that the speed of light, if you were to measure it, whether you move towards the source of light or away from it at constant velocity, you would measure it to be the same, which is very odd. Okay, this is something very peculiar about light. Because if you look at, say, an incoming car, and you run towards the car and you measure the speed of the incoming car relative to you, it would be faster if you're running towards it. But you run away from the car and you were to measure the speed, relative to you, then it's slower because you are escaping or opening up from the car. And even though the car is coming towards you, you are running away from it. And you will measure a smaller speed, right? So, but light is peculiar in that it doesn't matter you run into it or away from it, as long as you run at constant speed, okay, constant velocity, then you realize that you measure speed of light to be c, 3 times 10 about 8 meters per second. And obviously, I mean, this was, of course, clear from Maxwell's equations, which is the equations that tell you that light is made up of electromagnetic oscillations. You could see from Maxwell's equations for the propagation of the light waves that even if you did a translation of the coordinates, okay, in other words, like if you look at, trying to mathematically simulate the effect of measuring light when you change, the position where you measure it by a certain translation, okay, you will see that the equations are invariant also, the speed is invariant. So you could have seen that theoretically, but observationally, people have also verified that this is true. So that's the property of light. Okay, so people are wondering, okay, why? Yes, equations are right now in front of our face that it is like that. So Einstein said, well, let's forget asking why, this is the case with light. Let us just take this as a mantra that, okay, we accept light is this way. Let me relook everything that we know about mechanics. Okay, with this idea that light has a constant speed. Okay, regardless of whether you move away from it or into it. Okay, and as a result of that, the special theory of relativity was formulated. Okay, and that was in 1905. And so this is called a special theory because it is a theory, it is an updated theory of mechanics where there's no acceleration. Okay, acceleration is 0. There's no acceleration. Okay, so that is why it's called special theory. So he looked at half mv squared and all the very the well-known notions of mechanics, but without acceleration, with the consideration that light has this particular property. Okay, that whether you walk into it or away from it, you measure the same speed. Okay, and then he discovered concepts like time dilation and length contraction. So time dilation is essentially if you were to observe something that happens in a train that passes you very quickly, fractions of the speed of light, then you will see that the events of the train inside, the time will dilate. In other words, it will take a longer time for something to happen from your point of view than, say, a person who was inside. So that's like time dilation. Okay, the time dilates. And then length contraction is the same thing. You measure a rod, for example, inside a train that's passing you, it could be a certain length, but then for a person who's looking for it from outside and the train, as it passes you more and more quickly, the length of the rod starts to shrink. Okay, so then there is this. So the point is that time now becomes not absolute. It depends on who observes the time and where, in which frame are you, not the moving frame or non-moving frame. Okay, and even the frame that's moving, if you're inside the train, you could say the person on the ground is moving. So that's the reason why the theory is called relativity. Okay, and length, same with length contraction, same thing. So in that sense, okay, special theory of relativity tells you that time is no longer absolute, because time itself, the rate at which time can flow, also changes. So time dilation means time flows more slowly because it dilates. It takes a longer time to have 1 second tick. The clock ticks slower, right, as you observe the things inside a moving train. So, and the faster and faster the train moves, the time dilates even more. Okay, so you can see that time, the rate at which time flows, is speed dependent, speed of the frame that you observe dependent. So in that sense, time is a bit like a distance coordinate, whereby the rate of change of distance, the rate, depends on speed. Okay, and therefore time was then put on a similar, not totally equivalent, but similar footing to space. And therefore it was hence called space-time. Okay, so that is the reason for the notion of space-time. Right? People always just utter this word space-time, you know, but the reason is because now we see that time is not absolute. Its flow, its rate of change, rate of flow of time depends on speed, just like a spatial distance, a spatial direction, a spatial coordinate. The rate of change of a spatial coordinate depends on the speed of the frame we are talking about. So then it becomes similar to space in that way for time. Okay, so that's why I call space-time. And it also shows you from his equations of energy, kinetic energy, which eventually gives you E equals to mc squared, you know, that nothing can travel faster than the speed of light, simply because as you increase the speed of something, its mass also increases. Right? If you increase the speed, you can think of it as energy equals mc squared gives the equivalence between mass and energy. Okay, and so as you increase the speed, energy increases, mass also increase. So from there you can tell there's a limiting, there's a limit to which things can travel, and the speed of light is the limit, because before that, after that, the mass just goes to infinity, and there's no, you need an infinite amount of energy to basically, you know, speed it past light. Okay. Yeah. So then what happens? So if you look at Newton's law of gravity, the previous page, it says that this acts instantaneously. So as we know, all forms of energy, all forms of communication takes place, you know, through the communication of electromagnetic waves, okay, at least, right? Wave, you know, kind of thing. Yeah. And so Newton's laws of gravity need to be modified because it is in conflict with this latest theory of mechanics that Einstein discovered. Okay. And so then he went on to think very hard about this gravity thing. At the same time, simultaneously, he was thinking about how he can also generalize the special theory to include acceleration. All right. So, and then that was when he came up with the, or rather he was able to perceive the equivalence between acceleration and gravity. That was the crux of the general theory of relativity. Forget all the maths, that's just bookkeeping. The intuition behind the theory of gravity, of general relativity, is the equivalence principle between acceleration and gravity. Okay, that is the main thing. And so in a mechanics theory, which also included acceleration, you inevitably also include gravity inside. And then he has unified theory of gravity and mechanics all at once. And then the resolution to that conundrum between Newton's gravitational theory and special relativity, which tells us that nothing can travel faster than the speed of light, okay, is that gravity is not really a force, okay? Rather, it should be regarded as a deformation of space-time, the arena in which all physical events take place. So to give you a somewhat intuitive, but I won't say this is entirely correct, but this is what people use anyway. There's a more correct explanation of this, of what GR is about. But anyway, nonetheless, in the interest of time, I'll just show you what you always see in books. So let's say you have a planet here, okay, and in the past we used to think of the planet having gravitational fields and attracting, you know, things to it. But now you can see it as the presence of the mass here, which has mass energy. Okay, what it does is that it basically curves the space-time around it. And therefore, any object which travels, any object must exist in the arena of all events, right? Which is space-time. So, you know, when it comes near the planet, because of this curvature of space-time, then it tends to also change its path. Okay, it bends it. And so this is the effect of gravity, right? It's and therefore, once you have a model of gravity or understanding of gravity in this sense, where it exists as a curvature in space-time, then its effects are instantaneous because they were there already. There's no need to like mediate the thing. You know, there's no need to wait for the thing to happen. It's already there, basically, right? The curvature is there. So whatever effects that this path feels of the planet, it's already there. So there's no notion of time delay or a need to signal to the particle that it's being affected by gravity. It's already there. Okay, so it reconciles that conundrum with Newtonian gravity. Okay, so that's gravity. Then that was 1915. Okay, so 1915, right? Okay, 1915, right? And then after that, quantum mechanics took off in the 20s, you know, with a whole range of people working on quantum mechanics, contributing to it. Schrödinger, Heisenberg, Max Born, Paul Dirac, all sorts of people. And then finally from quantum mechanics, which is essentially the quantum theory of a particle, people needed to study a quantum theory of many particles, because the world is made up of many particles, and atom itself has like more than one particle, right? So it's got a proton, a neutron, it's got an electron, right? And atom has all these things. So we needed basically a quantum theory of many particles. And so that resulted in the development of quantum field theory. Okay, quantum field theory is the quantum theory of many particles, because once you have a field, a function, you can say at this point in space and time, there's a certain value for the field. So in the context of a quantum field theory, you can say at a point in space and time, we have a particle with that characteristic. Then it becomes a theory of many particles. Okay, and after understanding quantum field theory, people wanted to understand the interactions, like light, for example, electromagnetism, the forces. They wanted to understand the strong nuclear force. The strong nuclear force is what binds the protons in the nucleus together. They are plus, right? They're all positively charged. They should actually just repel and explode. But yet there's a strong force which keeps them, you know, bound in the nucleus. And that's a strong nuclear force. Okay, and then there are other forces, like say the electron, you know, aside from its electrostatic force that, you know, allows it to circulate around the nucleus and all that. There are other kinds of like beta decay, for example. There's some radioactive kind of processes whereby you can have energetic electrons that are ejected out from the nucleus and transform like a neutron, you know, into a proton, that kind of thing. So, and other kinds of things, the neutrinos and all that. So there's a third force, which is the weak nuclear force. Okay, and that beta decay, the ejection of electrons out of the nucleus, that's involving a certain kind of force called the weak nuclear force. Okay, so, and then so there are like, you know, people wanted to study these forces, and then came the idea of gauge fields. Okay, so the photon is an example of a gauge field, and the photon is the field which mediates the electromagnetic interaction. Okay, all these forces, electromagnetic forces. Okay, so, and then there's of course the weak forces, and you have the weak bosons, and then you have the strong bosons, the gluons they call it. Okay, and then so quantum field theory became quantum gauge field theory, and the culmination of like maybe I would say 50 years, from 1920 something to 1974, 50 years. Okay, and we finally have this standard model of the quantum world, which is our best model to date, most accurate model to date, to describe all the three other forces of the universe which involve the atom. Okay, so electromagnetism, okay, like I said, you know, is like the electron circulating around the nucleus by a attractive force of the proton. That's electromagnetism. The plus and minus charge type is electromagnetism. And then the gluons holding on the protons together, and then the beta decay shooting out electrons or positrons out of the nucleus. That's the weak nuclear force. So all this is in this standard model. Okay, and this standard model of the quantum world also tells us what are the basic constituents of matter, you know, up to the point where we can see them. I mean, to see smaller ones, we need to smash them more violently so we can see smaller bits. But as far as we can see now, which is about 10 to the power minus 22 cm in length, okay, these are the things, these are the particles, the zoo of particles that we can see. Okay, so you can see that at the quantum level, there are two types of, sorry, I'm taking a bit long. I don't know why I talk so much. But anyway, I think it's important that we just go through this. So there are two kinds of quantum particles. They are what we call fermions and bosons. Okay, so bosons are what we call things with integer spin. Okay, so integer spin is like, say spin 1, you turn around once, you see the guy once, back to its original. If it's spin 2, for example, it means a particle whereby you turn around one time, you see it twice. Okay. Now, then fermions are things with half integer spin. Okay, so they are quantum particles with half integer spin. Now, these are quite peculiar. So, say if you have a spin half particle, it means you must turn the particle twice around before you see it back again. Okay, so that's the spin half. So it's a concept which is a bit odd that we can't really comprehend in the classical world. But the quantum world, that is what it means. Okay, so essentially the fermions make up matter. Okay, they make up the matter of the world. Okay, all the things that make up matter, and essentially all the things in the atom which makes up matter, right? All the things in the atom, right? The protons, okay, the neutrons, the electrons. Okay, why do you not see the protons and the neutrons here? Is because actually when you take the proton and the neutron and you smash it, it's actually made up of even smaller things, and these are called quarks. All right, these are called quarks. They're made up of even smaller things and they're called quarks. Okay, and then electron itself, exists on its own. You can't break it down any further. Then the things, why are they called quarks? Because anything in the nucleus which involves being glued together by the strong force. Okay, so the strong force is the particle of the strong force, or the quantum, a particle of the strong force field is called the gluon. The photon is called the electromagnetic. The photon is the quantum particle of the electromagnetic field and the electromagnetic force. And the bosons, all these with integer spin characteristics, they are actually the particles that mediate the forces, the interactions. Okay, the fermions are the matter stuff. Got it? Okay. So these guys are all the guys that you can break up further, break the nucleus further. They're made up of things that make up the proton and the neutron. Okay, so in fact, actually, typically the proton and neutron are made up of the U and D quarks. Just this. These other things you can get in certain processes where you smash them even more violently. Okay, so and then the leptons are essentially things that are outside of the nucleus. Okay, they involve the weak force. Okay, so electron is outside the nucleus. Okay, and all these things also, these neutrinos and all that, which you see in processes in the sun. Okay, so the zoo of particles, not to worry, you can't remember. I don't remember them anyway all the time. Okay, so and then you can see there are three sort of families of these particles. Okay, that make up matter. And then in terms of the forces, the photon is the quantum particle of the electromagnetic field. The gluon is a quantum particle that gives rise to the strong nuclear force field. And then these three bosons here, there are three of them actually. Okay, there's the W plus minus and the Z one. Okay, so here these are the quantum particles of the weak nuclear force, the mediates weak nuclear force. Okay, all right. An important one is this thing called the Higgs boson. As some people may call it the God particle. Okay, so the Higgs boson actually is something that is of integer of spin 0. Spin 0 means it has no direction. Spin 1 is something like a vector. Okay, so spin 0 means it has no direction. It's a force field, or rather, it's not a force field. It is a field. It's a scalar field, which is present everywhere. That's directionless, but its presence gives the mass to the matter. And what is the consequence of having mass to the matter? Once it has mass and it's not zero, like no weight, it can actually bind. Okay, so what you see of the world, the fact that I'm made up of atoms that are actually stable enough to be bound and not flying everywhere, is because of the Higgs boson. The Higgs boson gives mass to the matter particles. Okay, the matter, the fermions, which are the matter particles, and therefore we are able to be bound together. Otherwise, we'll just be flying around. Okay, and it also gives mass to these bosons here, the weak force bosons. And in giving these weak force bosons mass, it will also mean that it limits its range of interaction, because if something is massive, its interaction range will be less because it's got to carry its weight. But let's say if a photon, for example, which is massless, photon is massless, that's why electromagnetic force can actually propagate over very long distances. But it's also the difference in the distance between how the photon acts and how the weak forces act that makes up everything that we see in the universe. Because if they were of the same range of interaction, the forces, then everything will change. Something off balance, and then that's it. Okay, you will not see the visible universe as it is today. All right, so it's very finely balanced, very nice. Okay, so that's why they call the Higgs boson the God particle, because of this reason. What you see of existence and everything in this world is really due to the fact that this guy here gives masses to the matter fields and gives masses to the weak bosons here, and therefore differentiates the range of interaction. Okay, so that is the thing. Okay, that was 1974. Now, why the need to unify gravity and the standard model? It seems like we know everything, as I mentioned at the start of the talk. We already sort of know everything, right? I mean, we have gravity to explain the cosmos, and we have the standard model to explain the very small things. And in between, we are using, electromagnetic theory is something you can use, over a large scale, like small things, big things also you can use. So pretty much all of engineering and technology, you don't really need a unification of gravity and a standard model. So why then do we care to unify gravity and the standard model? Okay, it's because we want to answer the biggest question that humanity has had since the dawn of civilization, right? Which is, what happens at the beginning of time? You know, what is the origin of existence? Why, how did we come about? Okay, people want to understand that. So evidence shows that we are coming up from a Big Bang. Okay, there's an inflation of the universe, and then there's relics of the Big Bang. So it must have then meant that if you de-extrapolate down to time equals to 0, it will mean that all of the visible universe that we see today is actually crushed into a single point. Okay, so like this now. So then why still a need to unify gravity and the standard model? The reason is the following. Now, if you take a pin and put it on a table, and you put a magnet over the pin, you will see that the pin is being attracted by the magnet, correct? That's something which we all have seen before. Okay, if you haven't, then I'll tell you that there's a fact. Okay, then you put a magnet over and the pin will be attracted. Now, the Earth is so big, you know, and the magnet is so small. So the Earth's gravitational pull on the pin cannot even overcome the pull of the magnet on the pin. So some people will say, yeah, it's a magnetic material and, you know, gravity, but gravity attracts everything. So it's fair to compare gravity's attraction with any kind of force attraction, right? Correct. So you put a magnet that's so much smaller, it can attract the pin. And the Earth, which is so huge, cannot, you know, attract the pin more than the magnet. So this tells you that actually gravity is a very, very weak force compared to the magnetic, the electromagnetic force. Okay, likewise, if you do other experiments, you know, with the strong and weak nuclear force, it's the same. That's why our lab experiments of things that involve particle physics, we can just ignore gravity and it won't matter because gravity won't affect anything because it's too weak. In the lab, it's just too weak to interfere with anything. So we don't care about it. Even when we make our phones and all that, look at our phones, you know, and all these, electrons and things, you know, flowing everywhere, semiconductors and all these quantum states. Nothing about gravity affects the function of the phone because it's a very weak force. It's there, but it's so weak, it doesn't interfere with all the other forces. So therefore, that's why we can coexist, or rather, we don't need to know the unification under normal circumstances because gravity doesn't affect our daily lives usually, okay? But when all of the universe is crushed into a single point, then that's when the density of material in the universe becomes very high. And you know, the gravitational field or gravitational effects of gravitational field are very strong, get stronger as the mass gets denser. So imagine all of the universe, everything, all the planets and everything all come together into a single point. That is extremely dense. Then the strength of gravity becomes very pronounced. Pronounced enough to be comparable to the other forces. That's why we need a unified theory of gravity and the other forces and the standard model to understand what happens at the beginning of time. Okay, so that is the main reason. All right. Okay, so that's what it means here, where gravity and quantum forces were therefore comparable. Okay, they are about the same, the strength. And once it's about the same, you want to understand what happens at a small point, you obviously need a quantum theory because that small point means it's quantum. So you need a quantum theory. Standard model is a quantum theory. Okay, and then you need gravity to be inside because gravitational effects can no longer be ignored in this quantum theory. Okay, because it will be very strong. Therefore, we need the unification. But there is an incompatibility. So the biggest incompatibility was the following. Okay, so Einstein's idea of curved space-time is that the curved space-time is fixed, okay, and it is smooth. But quantum mechanics tells you that at the quantum level, whatever observations of the physical world you make are actually not deterministic in that, you know, they exist in multiple states at the same time. Okay, there isn't one sort of particular state that it is in until you observe it, but until then, okay, so quantum mechanics is a non-deterministic theory, which tells you it takes a superposition of different possibilities at the same time. Then at the quantum level, it must mean that the space-time geometry must also take a superposition of different geometries at the same time. So that's incompatible with Einstein's idea of a fixed, determined, smooth geometry. So when you take many geometries at the same time that superpose in the quantum sense, then the space-time becomes rough. Then it becomes like a foam, basically, because it's only in a foam whereby you can say, oh, you overlap many different types of geometries and you add them and then it doesn't look even. Right? So quantum, at the quantum level, Einstein's theory is incompatible with the principles of quantum mechanics. And we know we ought to follow that because we're talking about quantum theory. So the quantum theory that things are a superposition of all possibilities at the same time, that surely must hold because it's a quantum theory. But the problem is we cannot bring Einstein theory into the quantum level. Okay, and when we are talking about such sort of foamy kinds of space-time where it exists, at in different superpositions at the same time, it's like the distance of 10 to the power minus 35 meters. Okay, or 10 to the power minus 33 cm. Okay, so 10 to the power minus 35 meters. Okay, so this is the gravity at very small scales tends to be foamy with all possible geometries occurring simultaneously. So that's an incompatible part of the theory. So people have been trying to grapple with that and they couldn't, okay, before this whole string theory thing. Okay, so that's one challenge. Okay, so I mean, further reasons why people think about, okay, wanting to overcome this challenge of unifying gravity and the standard model is the following. Okay, so as I mentioned, the strength of the coupling of gravity becomes comparable to other forces at the beginning of the universe when it was bang size. Okay, I have explained why gravity needs to be unified the standard model if we wish to understand the origins of the universe. I've also explained why. Okay, now quarks and leptons. Okay, remember quarks are the elementary particles that break down further of things in the nucleus, the protons, neutrons, you break down further, they become quarks. Leptons are essentially things that are, involving things outside the nucleus, which is the electron and all that, right? So they have different masses and there are many charges and coupling constants in nature, like electric charge E and Newton's gravitational constant, all of which you need to use experiments to actually figure out and then input into the standard model. So the standard model is one whereby it does not explain for you how these things have those values. Okay, so if we are to look for an ultimate theory, if we are to fully understand a theory, or rather arrive at a theory that is the ultimate theory, then all these things, all these masses, charges, and coupling constants that we observe in nature should be able to just naturally, from first principles, be derived from this fundamental theory, right? Okay, so that's the motivation for us searching for this final theory. Okay, so it's not unreasonable to expect that all particles and interactions to be a manifestation of the same fundamental identity. So the unified theory, the most fundamental theory, will be able to derive for you all these values of the masses and the charges and coupling constants. It should also unify the fermions and bosons into a single entity. Right, we saw the chart. There's fermions, which tells you all about the matter, and then the bosons, which tell you all about the force, the particles of the forces that they mediate. Okay, between the matter, right? The forces between the matter, and so that's the reason why people search, for this ultimate theory, because we want to be able to derive from first principles all these things and to unify fermions and bosons. Okay, that means unify in a single framework the matter fields and the force fields. Okay. So, all right, so just a history of the unification. So this is the history.
Oh, yeah. Into pressure.
Yes. Okay, so electricity, magnetism, and light. This was, of course, unified into electromagnetism by Maxwell. And then, as I mentioned, people discovered beta decay in the lab and neutrino interactions. And then this was formulated into what is known as the weak interactions. And then Abdul Salam, Steven Weinberg, and Sheldon Glashow, they unified this electromagnetism with the weak interactions into what we call the electroweak theory. Okay. And then at the same time, people were studying hadronic physics. Hadronic physics are physics of the particles inside the nucleus. Okay, so the protons, neutrons, and this thing called pions. Pions are essentially quark anti-quark pair. Okay, so they are just made up of the subconstituents of the protons and neutrons, but the itself and the anti-pair. Okay, and then so it's actually just physics of the nucleus. And then this is what is known as the strong interactions, because they involve the strong force field that keeps the protons inside the nucleus. Okay, the very, very strong, the gluon. Okay, it's a very short range force field because it only resides within the nucleus. Okay, and so we have the strong interactions, a theory of strong interactions, a theory of electromagnetism and weak combined into one. And so together, this is the standard model actually here. Okay, so this is where the standard model is. It is able to describe the strong interactions and the weak interactions. Then there are people who postulate that the standard model, all these force fields can be unified into a single force field, or rather a single force field in the sense that the strength of the coupling of the forces are the same for these two and this one. Okay, and that's called the grand unified theory. So when you hear people say grand unified theory, it's actually still not including gravity inside. Okay, it's just unifying the theory of the strong interactions with electromagnetism and the weak interactions to say that at a time in the universe when the energies are much higher, when it's still very hot, okay, and not cooled down as much, these three forces are actually manifestation of a single force with a single kind of coupling, single strength, and not different, different forces, okay, in the single force that does the work of electromagnetism, weak interactions, and strong interactions at the same time, basically, like in the same stroke. Okay, so that is the grand unified theory. Okay, so that is something which people tried to pursue also in the 70s. Okay, but yeah, so that's just still a theory. Okay, and then on the other hand, here, of course, back in the old days, terrestrial gravity, you have people like Galileo, studies kind of thing, terrestrial gravity, celestial mechanics, Newton. Okay, and then that came about to universal gravitation by Newton. And then Einstein brought in this whole thing about space-time in special theory of relativity, and then brought in acceleration with it, and then was able to merge gravitation with this thing here, a theory of relativity with acceleration, and then giving us general theory of relativity. Okay. And so now to unify this part here, the electromagnetism, the weak, the strong, and GR, that's string theory. Okay, so this is where unification is till today. There are, of course, other competing theories of quantum gravity, of unification, but they have all just worked in a very, very small way. So loop gravity is something that people have worked on, okay, which is starting from general theory here. They quantize general relativity, they quantize the gravitational field, okay? They try to quantize it by treating it like a gauge field. So that's something like loop gravity. Okay, quantum gravity normally talks about this. So quantum gravity means quantizing gravity. Okay, so, and then they try to do this. And then there are other small attempts to understand this unification, but none of them are as far-reaching as string theory. Okay, string theory is to date still our best hope at unifying everything. Okay. So remember we mentioned that we want to find a framework which treats the fermions and bosons as a single thing, right? A single entity. So then comes in the concept of supersymmetry. Okay, supersymmetry, whereby supersymmetry tells us that for every fermion that you have, it comes with a pair that is a boson. So then therefore you have like a fermion boson pair as a single identifier entity. Okay, so it comes in pairs with equal masses, right? So, but today in the lab, we have yet to observe the other super partners, super pairs of the things that we have. For example, electrons we know, okay, that is something we know, we observe. So by right, if the universe is supersymmetric, or the theory, the fundamental theory is supersymmetric, there ought to be what is called a selectron. Selectron is the super partner of the electron. Okay, it's going to have an integer spin. That's why it's a boson. And usually it's shifted by half. So, an integer spin here. This is spin half. Okay, and same thing. Photon ought to have a photino, which is its partner. The quark will have a squark. A gluon will have a gluino. So all those in dark print are things that we saw earlier on. Okay, and supersymmetry tells us that by right you should also have these super partners. But to date, we have not observed these super partners in the lab, but that's understood, that's expected. That's because symmetries, okay, are broken when you come to lower energies. Okay, that has got to do with the basic condensed matter concept of phase transitions. Okay, so if you look at the gauge fields, for example, remember in that previous diagram here, we talked about the grand unified theory, right? So today in the lab, we observe this independently, and this independently, and therefore our standard model is here. So why do people postulate like this kind of thing, whereby it's a single force that's so symmetrical that this, and this are together under one framework? That is because at higher energies, you can see that quantum field theories tend to be unifiable and the symmetry tends to be unbroken. Okay, so unbroken in the sense that it can all be encompassed into one kind of symmetry and not separate symmetries. Okay, not separate effects. Right? So the same thing is happening right here for supersymmetry. It is a symmetry that is only preserved at very high energies, that if you go to lower energies, the symmetry gets broken. And the consequence of a broken symmetry is that although fermions and bosons come in pairs, their masses no longer become equal. So that is the signature of a broken supersymmetry, that the masses no longer become equal. And if the masses are no longer equal, so what happens is that your electrons, photons, quarks, and gluons, that will remain the mass that we have observed. Okay, but the other guys, the partners, their masses will be much larger. So they diverge. Instead of having an equal mass, they become much larger. So at lower energies, these other partners start to gain a mass that's much larger. And to observe something of larger mass, if you go back to E equals to mc squared again and see the energy mass equivalence, it means you must conduct experiments with very high energies before the mass can manifest, can see it, can measure it, basically. Okay, so, and then again, our accelerators and our technology is not to the point where we are able to, see those energy scales that manifest these masses yet. Okay, and so this is an ongoing effort. People are finding it very hard to find these things because the masses are very high. So what people usually do is to find indirect evidence of galactic events. Because on Earth, our lab cannot simulate such energies, but in space, where there's a collision of some, planets or something, or some galaxies that merge, or some galactic event, that those energies are high enough because that's galactic. Okay, so sometimes we try to find indirect signatures of such things from galactic events. Okay, so there's still hope that we can actually verify this concept. Okay, so supersymmetry, right? So we have said what we need, and then now we will see how string theory comes to the rescue. Okay, so we have stated the things that we needed to do. We have stated the problems that we face. Remember about space-time foam. We needed something that was supersymmetric, that relates bosons to fermions. Okay, and so string theory is the main thing that will save us, or rather allows us to satisfy all those things. Okay, so before I tell you how it does so, I'll just explain to you what string theory is. String theory is as what it is. It's a string of energy, if you will. Okay, a string of energy. So what it means is this: in the past, when we used to see a point particle, propagating in space-time, you will trace out a world line, right? Now, what string theory tells you, the tenet of string theory is the following: that what looks like a point particle to you, if you look at it more closely, it's actually not a point, but it could either be this or this. Okay, for you to visualize what I'm saying, you can just think of it as follows. You take a pencil or a pen, you go to any wall or chalkboard, and you draw a very short dash. And then you start to walk further away from the chalkboard or the wall. The short dash will look like a dot to you. So what it means is that a string which is very small, from a far distance, it looks like a point. Okay, so all this time, when we did our experiments and only saw points in the lab, the protons are a point, the neutrons are point, electrons are point, for example, right? That string theory tells you that we didn't look close enough, not finely enough. Only 10 to the power minus 22, that was what we can see the distance from our experiments, right? If we were to look at a point particle close enough, then it will look like a string. It could be an open string, it could be a closed string. Got it? So that's it. That's all. That's what string theory is. It tells you that whatever we see, which was a point particle, is actually made up of a string, a very, very small string. So that means that if you were to draw say, a string that propagates in space-time, instead of a line here like this, you can see actually that if you look much more closely, it's actually like a tube like this if it's an open string. Got it? And then if you see another string, another point particle, which actually is an open string, okay, it really is an open string, then you will see a sheet. Also, if you look at it closely, it's actually either this or this that is being traced out in space-time and not just a line. Okay, so different things, like for example, different types of particles will be closed strings, different types of particles will be open strings. So whatever you observe as particles would either be an open or closed string in reality, or rather in reality and in finer, magnification. Okay, so that is the point, that's the tenet of string theory. It tells you that. Okay, now, how then does this solve the first problem that we saw earlier on? Okay, of what? The fact that gravity at the quantum level is very erratic, that is random, the geometry is foamy, so you can't say anything deterministic, or you can't have the idea of gravity, in that space-time kind of form. Well, if the smallest entity is actually a string, which is of a finite size, and the smallest entity is not a point, which is of zero size, it means the smallest probable distances, or the smallest distances that are even relevant to existence, must be that of the string size. And the string size is 10 to the power minus 33 meters. Okay, the Planck size has even lost more than that, it's 10 to the power minus 35. So the catastrophe of that indeterminate random space form that we expected, that is censored from a theory of strings, because the smallest thing is the string already itself. So then we don't have to go down to that part where the space-time becomes foamy. Understand? Okay, so that itself helps you. If you model it as a point at zero size, so it means you are looking at physics all the way to zero size, a point. So a point is essentially how small? Theoretically, it's 10 to the power minus infinity powers of a size, because a point is supposed to be just a point, right? And so we are not in that situation where we have to grapple with the effects of a foamy space-time anymore, because our smallest observable entity is a string. Everything, a graviton is also made up from a string. So the point is we are rid of that problem. Okay, we don't have that issue. Very nice, very elegantly. Other things, so I'll show you other things that compels you to, and that string theory is on the right track. Okay, other things. So let's just look at a string and see how a string, okay, can actually result in the particles that we observe. Okay, so we will be playing with what we call, rather we will be discussing what we call a superstring, because remember, we wanted supersymmetry, which means we want a unification of the bosons and the fermions into a single entity. So we must consider what is called a superstring. Okay, so a superstring has supersymmetry embedded in it, or rather supersymmetry that's constructed out. It obeys supersymmetry. So a superstring is one which has both bosonic and fermionic qualities of degrees of freedom. Okay, so what does this even mean? So bosonic, well, that's the usual degree of freedom, the usual things that we know about, just nothing. Okay, there's no need to define. You really understand intuitively what the bosonic degree of freedom is. Now, fermionic degrees of freedom, fermionic qualities, okay, means the following. Let's say you have two strings and they cross each other. The minute they cross each other, that degrees of freedom will flip. Okay, so in other words, let's say it was oscillating up and then you cross the string, you'll pick up a minus sign in its wave function. Okay, and that would mean that actually, it should be, instead of oscillating up, it goes down. Something like this. Okay, so that's the intuition, right, for the what it means to have a fermionic quality of a degree of freedom. Okay, so essentially the difference is between a normal string that is not superstring, purely bosonic string, is that when you swap strings in positions in space, okay, they pick up a negative sign in their dynamics. And so that is the understanding, that is how you can understand what a superstring is. Okay, so, and indeed, if you look at fermions, fermionic particles, they're the same thing, basically, right? They anti-commute in position, basically, right? So you flip, a spinner and then in position, and then they take up minus sign. So exactly a superstring behaves like a fermion. Okay, so that's the point. So there are two types of strings, open strings and closed strings, and a string can vibrate in an infinite number of possible ways. Infinite number of possible ways, right? Because of the modes and the harmonics and all those things. And the different ways in which a string vibrates would then, when you observe from far, give you the different particles. So electron is a certain string that vibrates in a certain way. The photon is a certain string that vibrates in a certain way. And from far, you see the point particle photon, the point particle electron. Okay, so that's how string theory can give rise to the rich zoo of particles that we saw, even the quarks and all those things. They're made of composite strings. Okay, strings that are bound together, that from far looks like a quark, for example. We'll see that later on. There's a picture of it. Okay, so this is what string theory is about. Right? So whatever we know of particle physics, if you look at the particles more closely, they are either made up themselves alone of strings that are vibrating with certain harmonics. That thus gives you, its mass, its charge, and all those things. Okay, the characteristics of things you see and observe can be attributed to the vibrations of the string. Okay, the specific vibrations of the string, right? Or they are made up of other particles that you see are actually made up of composites of strings. They are made up of strings coming together. Okay, but from far again it looks like a point particle, but at close it looks like made up of strings. Okay, so now the main thing which tells us that we're on the right track to unify gravity and the standard model is that in string theory, there is a closed string mode, or rather a closed string with a certain configuration. This is obtained by solving the equations of string theory, okay, and seeing what kind of strings can come about from the theory. And there is this closed string which behaves like the spin 2 massless boson called the graviton. Okay, so I'll just give some background. So when people understood the photon already as the quantum particle of the electromagnetic field, people wanted to understand what is the quantum particle of the gravitational field. And so the quantum particle of the gravitational field was called graviton. It has spin 2 in the following sense. If you look at a photon, if you look at a gauge field, you write it as a mu, for example. There's a small index, a tensor index called mu. So that's a spin 1 particle. But gravity, if you look at the metric, is g mu v. It has 2 indices. So that tells you it's a spin 2 particle. And the graviton is also massless. Okay. And that's why it's everywhere. Basically, it can go everywhere, just like light. It's far-reaching because it's massless. So the photon is massless. Graviton is also massless. So people knew how to characterize the quantum particle of gravity, but they could not formulate a theory of quantum gravity to have the graviton. They know what they must have, but they couldn't formulate it. Then comes string theory, whereby in the spectrum of possible strings, closed and open, and the way closed vibrates, you end up getting a closed string that actually from far looks like the graviton, the particle of gravity. Okay, and that was the time when everybody sort of jumped onto the bandwagon to study this thing. Because in its spectrum of possible vibrating states, vibrating strings, one of them is the graviton. It behaves like a graviton. Okay, and it's also massless. This mode of string vibration is massless. Massless particles in the string vibration just correspond to the lowest energy vibrations of the string. As the strings start to vibrate with higher energies, they will manifest themselves from far as heavy particles. Okay, so this one is a lightest mode of a closed string, and it corresponds to the graviton. Very, very nice. Okay, so this was the start of how people thought that this is the quantum theory of gravity. Okay, we have an idea of this quantum theory of gravity. All right. Wait, let me try to, I can't see the thing. Okay, yeah, because of things blocking. Okay, so then the other surprising thing is the following, okay? Extra dimensions. So fine, we found superstring. But then superstring also tells us that there are extra dimensions in the universe. So before people went on to the superstring, they studied the bosonic string first, which means the strings which, did not have this anti-commutative property of picking up a minus sign when you cross each other, okay? So they studied the usual one. But that's not complete, right? We always want to study the super version because we want a unified theory of everything. So usually in any kind of theory that we want to quantize, we start with the classical theory, write down a classical Lagrangian, observe the classical symmetries of the theory, and then when we quantize the theory, and what we mean by that For example, you put in a path integral. Okay, a path integral is Feynman's way of quantizing a classical particle. Put in a path integral, and then we start to observe the symmetries of the path integral to see whether it still obeys the classical symmetries or not. So when it doesn't obey the classical symmetry, we will try to find a way, a constraint, or something that we say the system must obey such that the symmetry classically ought to continue in the quantum level. That is our usual prescription of quantizing, a system. Okay, that classical symmetries being, why are classical symmetries should be observed? That's because quantum mechanically, when a particle is known to go to all possible paths at the same time, there is still a classical path that exists as one of the possible paths. And therefore, it means that the symmetries of the classical theory ought to also be conserved, when you quantize a theory. Okay, so that is the tenet of it all, right? So, and people do that once they quantize a theory, then they see that, there is a violation of the classical symmetry. And in the case of a bosonic string, the violation looks like this: d minus 26, where d is the number of space-time dimensions that the string can live in. So if you want that violation to go to 0, you must set d minus 26 equals to 0. And then indeed you get d equals to 26. All right. So of course, this was the first time we saw that strings needed higher dimensions, but 26 was a bit ridiculous, like so high. It doesn't make any. It's very counterintuitive to the 4 that we see. But we didn't need the bosonic string. We wanted the superstring because of the supersymmetry that we say should exist. And in the case of a superstring, that violation of the symmetry was d minus 10. So in the end, we got d equals to 10. Okay, still a lot, but it's gone down to 10. But you will see later on that very nicely, we have something that will fit, into a 10-dimensional space-time that will give us the 4 that we see. Okay, so it goes down to 10. So the point is that a quantum superstring tells you by sheer calculation, and it's not a postulate, it's not a guess, not like putting by hand, you're constrained by symmetries, that the space-time dimensions ought to be 10. Okay, so that was the first time people had a glimpse into existence of possible higher dimensions. Okay, but nonetheless, the time direction is still one-dimensional. That means time is still time. Okay, so last time we had x, y, z, and time. Now we have like x, y, z, and then 6 other spatial dimensions and time. Okay, so that is what string theory is about. It tells you 10 dimensions. So then why do we not see the other 10 dimensions or the other 6 dimensions, spatial dimensions? Okay, why do we see x, y, z and then know that time is there, right? Oh, what happened? What happened to the other 6 dimensions? So one possibility is the following. Of course, these things will be definitively proven later on once we understand string theory completely. At the beginning of the Big Bang, just imagine that the universe is made up of 10 orthogonal loops or 9 spatial loops. Okay, think of it as 9 spatial loops. All right. And then around the 9 spatial loops, 6 loops were tightly wound by strings. Okay, because it's very small, strings are so small, bound by strings. Later on, we know that just more than strings are also membranes. That's why I put membranes here. But think of it as bound by strings. During the Big Bang, 6 of these orthogonal loops, okay, there are 9 spatial orthogonal loops. 6 of these couldn't expand because the strings were wound around them very tightly. Then the other 3 spatial directions could expand. Okay, they could expand. And if you look at a loop, right, as the loop gets bigger and bigger and bigger, and you think of a hula hoop, for example, a hula hoop, and an ant that is walking on a hula hoop. So if you look at an ant walking on a hula hoop, the ant doesn't know, because it's so small, it doesn't know it's actually walking in a loop. It thinks it's walking in a straight space, a straight line. So the same thing for the visible universe. Where we are today, seeing straight x, y, and z coordinate, we are really actually part of a very, very, very big loop that expanded from the universe, the beginning of the universe, that makes up our so-called vertical, horizontal, and piercing through here the axis of x, y, and z. But actually, it's just a very small part of a very big loop. So that expanded to become the visible universe. Okay, whereas the other 6 spatial dimensions did not expand. So we can see x, y, and z because the 3 loops of x, y, and z have expanded very big into forming the visible universe. So where are the other 6 that didn't expand? So it means the following. It means that if you were to take any point, okay, in space-time, X, Y, and Z, at that point in space-time, X, Y, and Z axis intersects. If you use a microscope, I mean, you don't have such a strong microscope, but never mind, 10 to the power minus 33, or, very small, 10 to the power minus 32, minus 33, that you will see that there are actually still 6 of these loops which have not expanded, but they're orthogonal. Of course, you can't imagine them, you can logically deduce higher dimensions. Okay. So there are 6 of these that did not expand. Okay, so they are orthogonal, right? And so that is the premise of string theory. So they are orthogonal, and so we can see the 4 space-time dimensional Minkowski space, X, Y, Z, and T. Can't see it, it's there. And then the extra dimensions are curled up into 6-dimensional compact spaces, as I mentioned. So you take some X, Y, and Z, any point in space-time that you can observe, you go down small enough to the intersection of X, Y, and Z, you will see this 6-dimensional space as curled up. Okay, those are the spaces that did not expand at the beginning of the universe. Okay, so the final 10-dimensional universe is therefore made up of a product space of the M4, the Minkowski space 4 that we see. Okay, why Minkowski space? Because now after relativity, we have to convert the usual Euclidean space into Minkowski space to reflect the fact that time, the rate of change of time also changes as you change the velocity, the rate of change of your spatial directions. Okay, so that's why there's a Minkowski here. Okay, so this is 4 space-time Minkowski that we can see, and Y6. So you can think of the whole 10 dimensions as the following. Okay, we can see the plane here. Okay, you can think of the plane as 4-dimensional. Okay, representatively, and then orthogonal to the plane is this Y6. Okay, so it's all hidden. You can't see it, but the string can see it because it's of the size of the string. So when a string interacts with the Y6 here, then it will manifest as particles in the M4 that we can see, which has all its properties. Okay, so that's the point. So that is the point. So this 6-dimensional compact space, of course, it cannot be just any space. It must be, the space has to be such that once the strings interact with these 6-dimensional spaces that you can see, it will manifest itself from far away enough as particles that we observe that have the properties that we want. Right? So that is how we back engineer what the 6 space should be based on observations that in the 4 space, the particles that we have ought to be this, that, or whatever. Okay, so, and then remember, we saw the standard model table where we had 3 families of matter, right? Or what we call the 3 generations of matter. So we must be able, the string theory that we have that's correct, must be able to reproduce for us the quarks and then the leptons and all those things that we saw. Okay, and so that based on this and how the strings interact with the geometry of this 6-dimensional spore space, we have come to realize that this 6-dimensional spore space must be what we call a Calabi-Yau space. Okay, and these are just technical things. Euler characteristic is the topology of the Calabi-Yau space, and through the analysis of string theory, you can see that the topology of these spaces will give you the species of matter particles that the vibrating strings can manifest, and then we need 3 generations, and therefore as a result this Calabi-Yau space has the correct Euler characteristics of 6 to give you the interactions after the string interacts with it, 3 generations of fermions. Okay, and so, and also this Calabi-Yau 6-dimensional space, if it's Calabi-Yau, it will also help to preserve the symmetry that we were talking about of the quantum string. Okay, it won't violate it. All right, dimensions, when you have the right dimensions, that was analyzed using flat space too. But then when you add a space that's non-trivial, to the 6 directions, it might violate that symmetry that we're talking about. So d equals to 10 wasn't, d minus 10 equals 0 is not enough, because the changes in the geometry of the space in which you define a string will add other constraints into it. Okay, and then these other constraints would then result in the 6 space being a certain way, and then that is satisfied by Calabi-Yau. Okay, technically it's called the first Chen class of the 6 space must be 0. Okay, the Chen class is just a topological class that you can think of it as the gauge field strength, the F that you know of gauge field of your Maxwell's theory. Okay, that is mathematically called the first Chen class. Okay, so that is something like around that. Okay, so anyway, never mind this, I'll keep it simple. So how small is a string then? Okay, so how small is a superstring? So we say that if you wind around the thing and all that. So a superstring size is about 10 to the power minus 35 m. okay, just above the foam size, okay, just above the foam size. And it has a staggering string tension of 10 to the power 39 tons, okay. You look at this, tons is like a weight, right? Yeah, so you could think of it as this tells you that it's so massive that it needs a lot of energy from E equals MC squared to actually unravel or to do experiments to see it appearing, to break it down to see it, because it's very, very massive, okay? So it's very small, therefore you need to smash it very hard to see it, because the harder you smash something, the smaller the bits you can see, and the smaller, if it's small enough the bits, then you can see the string. Okay, so for example, you see when viewed at small enough distances, all elementary particles can actually be seen, to actually be made out of strings. So as I mentioned, right, even a down quark, up quark, those things that make up the protons and the neutrons, right here, look, they are made of composite strings. Okay, so they are made of composite strings here. So if you want to see this guy here, the strings here, then you got to smash this very, very hard until these guys all become loose. Okay, so that's the point. It's very small, so you smash it very hard. Okay, so that's the point. And the size of a superstring is this small. It's as much smaller than the atom as the atom is smaller than the size of the solar system. Okay, that is crazy actually, very small. So our hopes of actually smashing something hard enough to see it is actually in the near future, not yet. Okay, we need something that can generate very high energies. All right, but or see galactic events that will enable us to indirectly deduce, see from there, you know, what's happening. So of course, you know, we still want to test it, right? Obviously, we still want to test string theory. We don't want to say, oh, you know, because it's so small and we can't smash it and then we can't test it. You know, I mean, we don't want to do that. We still want to test it. So how can we therefore test string theory? So as we already mentioned, if you look at the strings from a far enough distance, they are essentially just particles, right? We observe as particles. So maybe what we can do is see the sort of corrections to the particles' behavior based on our understanding of string theory. Okay, so all this time we always knew them as particles, but now we know that we look at them more closely. They are not particles, but actually strings. Then we want to see what string theory can say that these particles ought to behave differently from how we understood them just as particles. Got it? So that's what we try to do. So we want to use string theory to see what are the different things that what other ways in which the particles ought to behave differently, which we couldn't predict when we just thought of them as particles. Okay, so like maybe we observe some different harmonics of a string and some corrections here and there to see how they can behave. They should behave at lower energies, and then we try to look for such signatures. So that's ongoing. Okay, so for example, you know, actual dimensions, there are people who do experiments to see if, like, you know, gravity is leaking out elsewhere, actual dimensions, that kind of stuff, you know. So we have experiments that try to test string theory indirectly. Clever experiments, okay, clever ways of trying to test it. So this slide, very wordy, but essentially just means this. You know, we already said that the very low energy vibrational modes on a string gives rise to massless particles, and from a far distance, on looking at the string, we are seeing particles, you know, observe particles, and we want to see whether string theory predicts any deviations from things that we didn't envisage when we labeled them, when we just model them as particles, and so we try to test for that. Okay, so we can still indirectly test for string theory. Now, even though we set out to understand one, or rather formulate one theory to unify everything, embarrassingly, people discovered that there was more than one string theory. So at that time, they call it the embarrassment of riches. Okay, because you are getting more, for the one time that you don't care to have more of one thing, you end up getting more of one thing. Okay, so that was you know, sort of known as the embarrassment of riches at that time. This was all in the 1980s. Okay, they discovered that there were 5 consistent possible superstring theories. Okay, and then these superstring theories were essentially, you know, closed and open string theories. So there are different types of string theories, the closed ones and open ones. So there's type 2A, type 2B, heterodic string, E8 by E8, SO32. Okay, so for the sake of some of my PhD students who are here, I will say this a little bit more. Okay, so yeah, so type 2A and type 2B, these are just strings. Okay, they are closed. They do not have gauge fields, meaning that they eventually do not give you in 4 dimensions after compactifying the 6 dimensions down there. Generically, they don't give you the photon, they don't give you the strong nuclear force, they don't give you the weak nuclear force. But nonetheless, as theories themselves, they are physically sensible. Okay, so phenomenologically, these theories are not viable in the sense that people don't study them to connect it to the real world. So, okay, fine, you got 5 physically consistent superstring theories, but not all of them are necessarily related to the real world. Okay, but they're still useful in their own way. All right, so these two are not, okay, generically not related to the real world because they don't give you gauge fields. Okay, they don't give you gauge fields, and therefore they don't give you the force mediators that we know and observe of the world. Now, the heterotic string is also a closed string, okay, but it gives you gauge fields. But it gives you this very big gauge field, E8 by E8 and SO32. So these are just gauge fields in 10 dimensions that have this gauge symmetry, okay? But there are ways to break this down into a smaller group. So the electroweak gauge field is labeled by what we call an SU2. And the strong gauge field is labeled by what we call SU3. And the photon is actually labeled by U1, basically. And SO32 and E8 by E8, you can find ways to break these data here down into the SU3, into SU2, into U1 through other unification groups. Okay, so the point is you can attempt to get the physics of the real world in 4 dimensions by compactifying this string. Okay, so this is the phenomenologically most sought after string, the heterotic string. Okay, then there are also open strings. Okay, this one has SO32, another possible string theory that people can study to get the kind of physics that we see in 4 dimensions. Okay, with the gauge group. So gauge fields are existent in our reality, so it must have come from either this or this. Of course, later on, people realize that there are ways to also get gauge groups from this, but I shan't go into this. It's called geometric engineering, where you play around with the 6 space and then you start getting gauge fields from there. But that doesn't matter. The point is that as a first understanding, these two are the phenomenologically viable ones. Okay. Now, if you look, there is a 2A, 2B, and then there's a 1 here. Now, what does this mean? It means that the amount of supersymmetry that exists in the string theory. Okay, so in 10 dimensions, these are all 10-dimensional strings. So n equals to 1 supersymmetry in 10 dimensions, therefore type 1. Okay, so technically it just means that in 10 dimensions, if it's n equals to 1, you have 16 supercharges, 16 supersymmetric variations of the fields that leave the Lagrangian invariant. Okay, so this is type 1, and these are type 2, you have 32 supercharges in 10 dimensions. The heterotic string is actually a type 1 string. Okay, it only has 16 supercharges also. Okay, so for those of you who don't understand what I'm talking about, never mind. My students are here, so I also want them to understand something. Okay, these are my PhD students who are doing string theory, so this is a sort of a mini course, revision course for them too. Okay, right. Now, very interestingly, okay, we come back to finding one ultimate theory actually. So in the 80s, there were 5 different string theories that we saw earlier on. And then in a landmark research paper, a landmark discovery by Edward Witten, and he was my postdoctoral mentor. Okay, yes, he has been my mentor for most of my life, and I studied under him. So he, in 1995, he discovered that these 5 string theories were actually the same, is unified under a single 11-dimensional theory, actually. So the number of dimensions of space-time is actually not 10, it's 11. There was an extra circle that was hiding somewhere, okay? And that if you look hard enough, there was an extra circle that led to an 11-dimensional theory, whereby when it went down to 10 dimensions, it will go to any of these 5, via dualities. It related to any of these 5 via dualities. Okay, so that is M theory. So if you look at type 2A, 2B, type 1, and SOC, these were the 5 that we discussed earlier on. Okay, and then it is unified under a single umbrella by an 11-dimensional theory, such that from 11 dimensions, if you shrink the 11th circle to 0, you can go down to any of these 10-dimensional string theories via dualities. So it's actually one unified theory. So we came back to the original goal of getting one unified theory. Okay, and that was discovered by Witten in 1995. Now, where was this guy here, this outlier here that you see, 11D supergravity? Okay, so before string theory, the people who were trying to find a unification of gravity with the standard model worked on supergravity. So supergravity was the most ambitious point particle theory that tried to marry gravity with the standard model, but in the framework of still assuming that things are just points and nothing else. The smallest things are points. Okay, and this was done actually in the late 70s and early 80s, just before this whole string theory revolution picked up. This string theory revolution of finding the 5 string theories was in 1985. And then 10 years later came M theory. So a decade later, M theory was discovered to unify all of them. And this guy here was the hottest topic in research. I mean, the brightest people in theoretical physics were working on this. These were like the string theories of the day. They were the supergravity theorists. Okay, so they were trying to unify everything using supergravity. And they found that supergravity, again, was consistent in 11 dimensions. Of course, there are lower dimensional supergravities. There are 10-dimensional ones or so. But there is a 11-dimensional supergravity that in some sense also kind of unifies all the 10-dimensional supergravities. Okay, similar kind of story going on. Now, the nice thing is the following, that M theory, which is 11-dimensional now, when seen at the low energy limit, means far away. In quantum mechanics, in physics, when you say something is low energy, it equivalently means that you're looking at something from a far distance, okay, a long distance. If it's high energies, you're looking at things at a very close distance. That's why high energy physics, you're looking at things which are very small, distances which are very small. Okay, so if you look at things which are very far away, it's actually low energy. And so at low energies, where M theory becomes its point particle limits, where you look at it as a point particle, just like the other strings I mentioned, then it actually reproduces for you the things in 11D supergravity. So it means that whatever people did in the late 70s and early 80s of trying to unify gravity with the standard model, they were almost there. The only thing is that they didn't take the next step to say that it's not a point particle, but it was a string. Okay, there are some problems here. By adding the gravity, it becomes non-renormalizable, and basically you get answers which blow up to infinity. Essentially, it's not consistent. Essentially, you can't put gravity inside to give you a consistent theory. But the nice thing is, whatever work that people did in the past of trying to marry gravity with the standard model in the late 70s and early 80s, this whole thing here will reduce to that. So M theory in 11 dimensions, in the point particle limit, you'll reduce to 11 dimensional supergravity. Then type 2a and type 2b will also, in its point particle limit, also reduce to the supergravities of the similar names that people discovered. So it's consistent. So what people did back in the late 70s, now we postulate everything to be strings instead of point particles. When we reduce, and rather when we look at the string theories from far enough distance, they end up looking like those point particle theories that we're trying to construct or we constructed. But those point particle theories that we constructed were inconsistent in that they were not normalizable, meaning that if you were to compute certain physical quantities, they just blow up basically. Okay, and so, but once you think of these point particles not as points but as strings, like in this case, it becomes well behaved. So the transition is very natural that we should abandon the idea that things are made out of point particles but are actually made out of strings. Okay, because the string theory itself rescues you from all the problems of the supergravity theories that people had, the 10 and 11 dimensional supergravities that people had discovered in the 70s and the 80s, early 80s, trying to unify everything. Okay, so that's where another compelling reason for string theory comes from. Okay, and the string theories themselves, as I said, okay, they are related to each other by duality. So M theory, or what we call the mother theory, 11 dimensions. Now, if you shrink the 11th circle down to 10 dimensions, then you can see this guy is related to this guy by what we call T-duality. And then if you shrink M theory down on half a circle, S1 mod Z2 is half a circle or an interval, you can get a heterotic string, which is then T dual to this, and then this guy is S dual to this. And then if you go down another dimension, means you take the 10th dimension to be small again, and these two guys are also related. There is a zoo of dualities that relate all these 5 string theories, which ultimately are connected by the 11th dimension up to M theory. As the 11 dimension gets bigger, the circle gets bigger, then you have 11 dimensional theory. And if the circle gets smaller, you come down to 10 dimensions, which are then related to all these things. So it's in this way that M theory becomes the mother theory that sits on top of everything. Okay, never mind this first. I'll talk about this in a while. Okay, so there are two ways in which you can go down to 10 dimensions. Either the 11th dimension is just a circle. A very big circle is, of course, a straight line. Okay, so a huge circle is a straight line. And then you can go on half a circle. Okay, which means if you expand it, it's going to be a straight line with a boundary, with a start, and not like minus infinity and plus infinity, just 0 to infinity, for example. Okay, so you have a boundary here, right? And then it goes on the heterotic string. Now, what's T-duality? T-duality just means that if you have another smaller circle in 10 dimensions going down to 9, then these two guys are related in that this guy on a circle of some length is equivalent to this guy on a circle of a bigger length, the inverse length. Okay, so T-duality is just this. Okay, so it means that these two string theories are equivalent if, let's say, within the 10 dimensions, they have one direction which is still compact like a circle, then they're equivalent to the other one with a circle whose size is the inverse of that. So that's T-duality. Now, S-duality is just a higher dimensional notion of electromagnetic duality in Maxwell's equations. So if you put monopoles in Maxwell's equations, the E and the B, and you swap the thing, right? Yes, that's electric magnetic duality. So there is a higher dimensional notion of that, and that's called S-duality. Okay, so this guy is dual on itself. Okay, and then this guy is T-dual, and these are electromagnetic dual to each other. So you can see all these things that we saw just now in 10 dimensions, they all are related to one another. Okay, now, so the other thing which tells you that strings are on the right track. So if you look at quantum field theory, we have this thing called the Feynman diagrams, which look like this. So if you have a particle that scatters and then comes off like that, these are virtual particles. There's a Feynman diagram, you know, that can represent the scattering of the strings in this way. Okay, and if you look at this Feynman diagram, right, the Feynman diagram came about from actually looking at the computations that one needed to do in computing what we call the scattering amplitudes. So in quantum field theory, we want to compute the probability that a certain scattering event will happen, and that is some integral over something. And usually the integral is problematic in that it can give you infinite value, okay? And that is where the whole theory of renormalization comes about, to so-called, you know, sweep away the infinities of this integration to give you a finite answer, okay? And so the problem, the thing that plagues this calculation that gives it infinity are these points here. Look, if you look at this diagram, right, the arrows and the lines meet at a point. And in the integration, whereby this picture represents, you have in the denominator a distance between this line and this line. Now, at this point, the distance of the lines goes to 0. So we have something like 1 divided by 0. But 1 divided by 0 is infinity. So the computation becomes nonsensical. It has infinities in it. And then, you know, Schwinger, Tomonaga, and Feynman, they won the Nobel Prize for that. They found a technical way to actually solve this integration to infinity. So they imposed some limits and all that, blah, blah, blah. So essentially what they did was they found some way to circumvent this problem, okay? So that the point is that it's a problem, and they just found a way to circumvent it. And how they circumvented that way? They essentially changed the computation to censor this part where they meet. So they basically just look at the computer. This part is like a black box. This part is like a black box. They see the ins and outs, and that's it. And then they compute the answers by censoring this part of the computation. Okay, roughly speaking, that's what normalization does. Okay, and so then they don't get any infinities. So they have to deliberately do something like that, which is very unnatural. But now, if things were strings and not point particles, instead of this diagram, you'll get this. And notice that this never ever meets at a point, never. Because the smaller size of a string is still an extended size. It's not a point, basically. It never has the 1 divided by 0 in the denominator. You will never get it. Okay, which again tells us that this is the right theory to think about. Not a quantum field theory of point particles, but, you know, quantum theory of strings with a minimal size, okay, extended size. And then you won't get all these infinities that are plaguing quantum field theory. As you know, as a far-reaching and as useful quantum field theory is, it has all these problems. and people just swept them under the rug, literally, like, practically swept them under the rug, and and to get answers. But now in string theory, you don't have to do any of this. It's natural that this never happens. So this is the next compelling reason that we are on the right track of nature if we assume that they are strings, or we hypothesize they are strings. Okay, other things also, much more elegant things coming out, which I won't cover here. Okay, so people say, okay, we have strings and all that, but can we also have other higher dimensional objects? Since, we have strings in 10 dimensions, because 10 dimensions allows you to have more directions, right? So can we have like higher dimensional objects? The answer is yes. We can have branes, basically. Up to 9 spatial dimensions that we can have branes that are going up to 9 spatial dimensions. You can. And these branes are essentially, boundaries whereby open strings can end. So you have open strings, and then you have these branes that are high dimensional, and then the strings can actually attach themselves to it. Okay, so you can have high dimensional branes. Type 2a and type 2b strings show solutions in their spectrum of high dimensional objects other than just strings. Okay, they have branes, and they have branes of all sorts. Very interestingly, branes are there. Now, they are very, very massive, so they can't move around. Okay, they're solitonic. It means they are stationed in some point in space. So if you look at a world volume, they call it world volume, not world line. In space-time, it's just going up in the time direction, because time still flows up, They are just somewhere in XYZ, for example, okay, on nine spatial dimensions. Now, see, branes exist, and the interesting thing about the presence of branes is the following. Now, you have a closed string, they can hit a brane, and energetically, they would, break up into an open string when they go inside. Not all, but most of them. Okay, and then the open strings that broke up inside, they can combine together with each other and then be emitted out of the brane. Okay, so this phenomena that we understand of strings impinging onto branes has a very non-trivial consequence that can help us to explain in one possible theory why gravity is such a weak force compared to the rest. Okay, we will see this in a while. So before we continue to see that, we have all these possible configurations for string theory with the branes inside. We can have the strings attaching to the branes itself, or we can have strings that attach from brane to brane, or we can also have branes that end on branes. Okay, that's also possible. All right, so we can have all possible configurations. Now, so as I mentioned, okay, type 1, type 2a and type 2b have all sorts of branes. Okay, there's a 0-dimensional brane, 2, 4, 6, 8, even dimensional branes, basically. Now, type 2b has odd dimensional branes. Okay, 1-dimensional brane, 3, 5, 7. 3 plus here just means it's self-dual in the electromagnetic sense. Okay, so a 3-dimensional object has a 4-dimensional potential field, a 5-dimensional field strength. Electromagnetic duality in 10 dimensions is Hodge duality. That's a 5-form field strength that you go down again to a 4-form potential and a 3-form object. Okay, so that this statement, if you don't understand, never mind. It's meant for some people in the audience here who should understand this. Okay, and it's self-dual in that sense. Okay, so that's type 2b. Anyway, okay, so type 1 is an open string theory, so it must have the branes because the open strings must end on the branes. And you see this interesting, very peculiar -1d brane. So this brane is -1 dimension. And what was this -1 dimension thing? Okay, so these dimensions here represent the spatial dimension. That means this has got 1 spatial dimension. So if you add the time, it will trace out a sheet. Just like a string has 1 spatial dimension, in time it will trace out, in space-time graph, it will trace out a worldsheet, correct? Right. Now this -1 guy, what happens? So it's -1. You add the time direction, it is a point in space-time. This is what we call a d-instanton. So instantons are configurations which are just a point in space-time. So a point itself is a point in space, not space-time. If you draw it on a world line, it's actually still a straight line in the time direction. Because when you put a point particle on somewhere x, y, and z, time still flows, right? So if you have to draw its path in space and time, the axis, it will still trace out a straight line along the time direction. But this guy here, this -1 guy, after you add in the time direction, it becomes a 0-dimensional space, 0-dimensional object in space and time. So it appears only at a point in space-time. So it appears only at an instant. Okay, so a point in space-time, a point in the time axis means it only appeared for like now, like what, like 1 second, that's it, and disappeared, gone. It doesn't, you don't see anymore. And that's the origin of the name instanton. So this is a D brane, and therefore it's called a D instanton. Okay, so when you read D instantons, when you type to be string theory, it means this. All right. And so these branes, very interestingly, they're high dimensional. And remember, we had the 6-dimensional spaces that are very small, right? So these branes can also wrap the 6-dimensional spaces that are very small. Okay, because within the 6-dimensional spaces, there are spheres or smaller dimensional spaces that are within the 6 dimensions. And these branes can actually wrap them. And once these branes wrap them, they can also interact with the strings because they also have charge. And then for example, let's say you have a 4-dimensional brane that wraps a 4 space in the 6 space, 4-dimensional subspace of the Calabi-Yau manifold. Then it will just be left with no dimensions in the other 4 big dimensions that we see. So it will appear to us as a point. And then this point can also manifest as the point particles that we see in our normal particle physics. So the point particles that we see in normal particle physics could have an origin in the branes also, which wrap the other dimensions that eventually leave no dimensions in the ones that we can see, and therefore they look like point particles with no extended dimensions. Okay, so that's very rich, right? Just to tell you how we geometrically engineer point particles from branes wrapping around the Calabi-Yau. Okay, so now, but more interestingly is the next thing I'm going to say. There's this thing called the brane world model. Okay, very interesting. So that is an alternative candidate of our universe to the Big Bang theory. Okay, we'll discuss this next. Right, so this part here, string theory and the universe. So we already said the actual 6 dimensions of space are very small. That's what we postulated, right? At the Big Bang, they couldn't expand and they're very small. Actually, this is just one possible postulate. There is another theoretical possibility. It's not settled yet which one is realized because we haven't understood string theory fully. Okay, the actual dimensions, we assume that they were small, but it need not be the case. It need not be the case. It may just be that we can't see them because anyway they're orthogonal. So there's no way we can really see them anyway. We can't see them because they're orthogonal anyway. Okay, so they could have been big actually. In other words, we didn't have a Big Bang, but we existed just as it was, not like a Big Bang. Okay, and that is another possibility of how we can see the universe, like this here. So we know from type 2b string theory that we have 3 branes in the 10-dimensional universe, okay, or 11 up to M theory. Okay, we know it's hiding there. So think of these as the 3 branes. Okay, now the directions along the brane are like our visible universe, X, Y, Z, and then T is somewhere. Okay, T is somewhere else. Okay, somewhere else, T. So X, Y, Z is here. Then orthogonal to this, perpendicular to these branes are the other 6 dimensions. Of course, we only see one direction here, but we can logically deduce the other orthogonal directions as the other 6 directions. So essentially, what we're saying is that our universe that we observe is actually in this D3 brane here. Okay, and that there are many universes. So this is like a theory of parallel worlds, if you will. Okay, many parallel worlds, the brane worlds, they call it, right? And so we are able to observe, let's say, the point particle charges of our universe simply because we have open strings whose points end, on our universe. Okay, so essentially now we are saying that the points that we see really are points of the ends of the string. Okay, and that the external dimensions of the string are actually in the orthogonal directions. So this is the other postulate. Okay, so the ends of open strings appear as point particles in our universe. Now, more interestingly is the following. So we already saw that gravity is a very weak force compared to the other forces, the other 3 forces, the strong, weak, and electromagnetic force, right? And so what is the reason that gravity is so weak if, let's say, we don't have the idea of the Big Bang, whereby it was once strong, then now it becomes weak because it gets diluted. Okay, without the Big Bang, how do we then explain that gravity is so much weaker of a force? Okay, then this is the explanation. through this model, we have this explanation. So in the brain world scenario, on the brain world model, we have this brain here, we have this brain here, okay, and usually the two will be closest pair, right? So you think of the pairs that you take. So there's D3 brain and a companion D3 brain. So we are living here inside this brain here. Okay, now remember that closed strings, now the graviton, the mediator of the gravitational particle is the graviton. It is made up of a closed string, as we saw earlier on in the lecture. But what do we say about closed strings when they impinge onto a brain? Energetically, they break up. It's more favorable for them to break up into an open string. So once they impinge onto this brain here, our world, they start to break up and become open strings inside. So open strings actually do mediate the other forces, the strong, weak, and the electromagnetic force. They are made up of open strings. Okay, but so you see a lot of open strings, but you see very little closed strings because very few survive the boundary and not get broken. Then it explains for you that why gravity is so much weaker than the other forces, because there are very few closed strings which then have a chance of being the graviton, but there are many, many open strings because they are being opened up by the closed string hitting the brain that will enable us to that have a chance of modeling the other three forces of the universe that we observe. Okay, that is why gravity is so weak, because closed strings are not energetically favorable to survive past the brain boundary into our universe. But outside, yes, they can. So in the context of string theory, you know, gravitons are as numerous as the open strings which model the other forces, the gauge fields. Got it? Okay, so that's one explanation of how gravity is weak. This is a very nice, elegant model that explains that without having to think about how the strength of gravity becomes diluted as the universe expands and the symmetry is broken and all those things. So that is one way. That could be true, okay, but this could be true too. Okay, and so the closed strings that come here and are also supplied by these guys where the open string starts to merge and comes out as a closed string and gets propagated next to this guy. Okay, so this is how the process goes on. And then the other possible cosmological model, aside from the brain world scenario, aside from this one, is the cosmic brains, the collision of cosmic brains. This one also very interesting. Also open, we don't know which one is correct yet. So if you remember M theory, when we compactified on a circle S1, we got down to type 2A string theory, right? But remember we compactified on the half circle, the S1 mod Z2, right? That just means taking a circle and folding it into half. Okay, and that is a half circle basically, or rather, you know, almost an interval, if you will. So if you do that, if you take M theory and then postulate that the 11th dimension is actually, you know, an interval, a half circle, okay, equivalently a half circle, then you get this thing. Okay, so consider 11-dimensional M theory on the manifold with an open interval. So this is like the half circle. Okay, you can think of it as a finite line, half circle, then cross M6, cross Y6. Now, on the half circle, okay, in the rest of the 10 dimensions, you will get this, you will have this configuration, which is the 10 that we saw earlier on before we discovered M theory. Okay, and in this case, indeed, the 6 dimensions are small, okay, and everything we said earlier on before the brain worlds still holds. But you have 2 such copies at the end of the ends of the 11th dimension. Okay, you got 2 copies at the ends of 11 dimensions. Okay, and therefore, instead of many parallel worlds like in the brain world scenario, we have just one parallel world. So one copy of ourselves on the other end of this 11-dimensional theory. Okay, so it's called cosmic brains, they're 10-dimensional. Okay, so bottom line in these 10 dimensions was exactly the same thing that we saw earlier on, whereby 6 are curled up in the Calabi-Yau. The M4 is essentially, you know, the Markowski-4 space. Okay, and this universe, okay, unlike the brain worlds one, which was nothing going on, it's just static like this, nothing going on. This model actually marries the 2 concepts of parallel worlds and the Big Bang. Okay, and in my opinion, this is probably the most correct model. Okay, because it sort of encompasses all things that we know to sort of be true, right? Inflation and all these things. Okay, so this cyclic, but it has one only difference is that it is cyclic. Okay, so it has no beginning or end. Okay, so to understand it, we must look at it. again. So these are the two branes. Now this is the interval we're talking about, right? The distance here is the interval. This is 10 dimensions. 10 dimensions, this is the 11 dimension, which was S1 mod Z2, or rather equivalently an interval. So this is the energy potential graph. You take a negative of its slope, you will see the direction of the force. Okay, so you can see here, this slope is positive. So negative of this slope means it's a negative number, and force will be therefore in the negative direction. So it's pulling it here, and same thing here, it's pulling it here. But when it comes close enough, the slope becomes positive, so the slope becomes here is positive, so therefore it becomes negative, so you push it this way, and then this becomes negative, it will be positive, you push it this way. Okay, in short, basically it's like that. Okay, you'll just attract each other, and then after, when it comes close enough, they'll repel each other. Okay, and then that will tell us the following. Okay, so first it will attract each other, so there's a flat empty universe. So this is 10 dimensions. Okay, then it starts to attract, and then the ripples start to form. So the things that we see in the early universe, okay, start to form here. Okay, and then it collides almost. Okay, not totally, because totally the force of repulsion is infinity, and then after that, it collides, and then there's a big bang. So we observe the universe, and there's a big bang here, and then that looks like a big bang to us. Okay, and then after that, then it will expand again away from each other, and that's where we observe the early universe. Okay, it starts to cool down, and then cosmic expansion, it starts to cool down further. Okay, and then it comes to this point where we see the current universe. And then, because it continues at this point to still repel, we see the effects of repulsion on your dark energy, basically. Okay, and then when it goes far enough again, the potential characteristics such that you pull each other back in, and then you start the whole cycle. So you can see that this model is very nice. It's in line with all the things we studied about string theory in 10 dimensions, of 6 dimensions being small, and then the other 4 are being large, and all those things. So it doesn't throw away all those things, that nice things that we had. It explains the phenomenon of Big Bang. It can explain the phenomenon of dark energy, the repulsion, and inflation, basically. And so this model is actually very nice. I think it's probably the correct model. Okay, so it's yet to be determined. I don't work in string cosmology, but we should check with our colleagues on that. So the cyclic universe. So this happens again and again. The only difference is that in the Big Bang, there was a start and an end. That's it. But in this case, there is a cyclic universe issue whereby situation whereby it happens again and again and again and again. So it's a Big Bang, a big crunch, a Big Bang, a big crunch, and goes on and on and on. Okay, so this is the only difference, and a few other differences which we can predict. So it also gives different predictions compared to the usual Big Bang model on the black body, cosmic microwave background. Okay, so there are some differences, and what it means is that we can actually test to see if this is correct. Okay, so it's different enough from the Big Bang predictions of the Big Bang theory, such that we can actually test to see if this is actually correct. Okay, so this is very, very enticing, very nice. Okay, so these are some features of how this is different from the Big Bang. I'm running a bit short of time. It's a bit long. I could still talk, but I know most of you are quite tired already. So let's just quickly, briefly go through this. So yeah, its singularity is not as great. Okay, its collision temperature is finite. Okay, 10 to the power 23 Kelvin. Big Bang is supposed to be infinite temperature at time equals to 0. And there are no exotic relics in the cyclic theory, since the temperature of the singularity is not high enough to produce primordial black holes and monopoles. Okay, so these are the differences, and you can test for these things that are different to see whether this theory is right or not. That's the nice part. Okay, so in summary, we can say the following. Okay, so we have gravity here, which is a classical theory, and then we have a standard model which tells us everything about the quantum. Then we can marry the two here and get a superstring, okay, which solves the infinity problems of this guy and also brings in the graviton from this guy. So we can have an open string, we can have closed strings, we can have branes. But this guy here, independently, even without string theory, you could have developed in cosmology. People studied all sorts of cosmology, the Friedman universe and all those things, and so that developed on its own. But once you add in the branes, then you can have brane cosmology. And then you have colliding branes and such things called brane cosmology, whereby you can have a string theory understanding of the universe and how it began and how it will end. Okay, so that's very nice. So this is the summary of all we have done so far. Okay, so we go on to the last part. Okay, string theory and 21st century mathematics. I think for the purpose of the rest of the audience, even though my students are in the audience, I won't say too much about it. Okay, you have any questions, you can ask me later on. Okay, but the point is this. So this is an area which I work on. So I specialize in this. Okay, so string theory has a very wide spectrum of work that people can work on. Okay, so there are people who work on string cosmology, which is what we saw, the brains and all those things, the things which are most popular with the lay person. Okay, and to me, it's still very interesting. That's one of the reasons why I got into this anyway, to understand the biggest questions about the universe. But on the other end of the spectrum, the more technical end and the more demanding end is also, string mathematics, which is how string theory interacts with 21st century mathematics. For myself, certainly it wasn't something that I wanted to get into in the beginning because, I wasn't interested in maths, I was interested in physics, right? So, but then as you start to understand that physics can actually give rise to new kinds of mathematics, now that's a different thing. Okay, you're not studying math now, you're creating math. Okay, so that's a different thing. Now, when you come up with the new math concepts, that's a different thing. Okay, and so I will explain to you how this comes about, string theory and its influence on mathematics. Okay, so research in string theory and its related supersymmetric quantum field theories. Okay, so what I mean is, string theory, when seen from afar, it's a point particle theory, so it's a supersymmetric quantum field theory. Remember the brains that we saw, the D brains and all that? Inside the D brains, right? Remember that the open strings can end on the D brain and they're like points, right? So inside the D brain, the points that they see, there are no strings inside already. There are points sometimes, the open strings can go in, but sometimes the strings just end on the D brain and they form points. The point particle theories inside the whole volume of the D brain, they are also quantum field theories, and you can study those also. So the string theory itself and its related quantum field theories, as what I just mentioned, has actually invigorated and expanded fields in pure mathematics, such as the following. Okay, algebraic geometry, differential geometry, algebraic and geometric topology, number theory, representation theory, and integrable systems. Okay, so if these things look foreign to you, never mind. Okay, in the interest of time, I'll just sort of illustrate roughly. The message is that it's broad ranging. This is almost every topic in Maxwell. Okay, and so it has invigorated, expanded these fields through an emerging third discipline called string mathematics. Okay, so string mathematics is, I would say, like as I mentioned many times, from studying the mathematics, from studying the physics of string theory, using physical concepts like conservation of energy, stability of minimal energy states, electromagnetic duality that we saw earlier on, T-duality, these are all physical concepts. Okay, T-duality actually is also energy conservation. You're computing the Hamiltonian of a string theory, whereby the circle is of a different size, and you realize the Hamiltonian is invariant when the size of the circle gets inverted. Very interesting. Okay, and then that just means your energy is equivalent. And from there, we postulate a physical duality of string systems with different sizes of the circles. Okay, so it boils down to energy conservation. So these are things which we learn very first time we learn physics. We learn it already. Electromagnetism, they are a pair. Okay, yeah, we learn that. Energy conservation, we learn that. Energy states, minimal energy states are stable. Well, we also learn that in the principle of least action. We also learn that. So all these things also appear in the context of string theory. And the miraculous or the most interesting thing about it is that applying these, very basic concepts that we already knew from way back when we studied physics, it will give rise to new mathematics. And the reason why it does that is because the quantities that we compute, the basic quantities, the rudimentary quantities that we compute in the context of string theory. Say, for example, we want to compute the energy of a string system on this 6 space. The expression of the energy function involves sophisticated mathematical expressions. That's because it's a string theory and not a simple quantum mechanical theory in 3 dimensions. Okay, because it's high dimensions, it involves a Calabi-Yau space, it involves topology. So when you want to compute the energy of a string, in this kind of configuration, the answer comes out to be something sophisticated, involving sophisticated mathematics. And then that after the string goes through a duality, the string system goes through a duality, energy must still be conserved. Then you compute the energy again in the transform or the after duality's transformation, the string system. And that expression for the energy will also come in a sophisticated mathematical expression. Then by energy conservation, you equate the 2 expressions together. And then you realize that you actually got a new mathematical identity from the physical principles. And how do we know it's right? Of course, the very first few pioneers that did this, essentially people like Witten. Witten was, in some sense, the first string mathematician. He was the first guy to sort of do this kind of thing, use like physics to get new mathematics. And the other people that followed, his descendants and all that, okay, other people, my seniors basically, okay, the predecessors, yeah. So they also did those kind of stuff, and I also work in this area because I'm in that school of research, and so people start to give these equalities to mathematicians and tell them, look, maybe you guys want to check it out on your own using your own rigorous ways of calculation, just breaking down the calculation with no physical input to see whether it's correct. And time again, they are proven to be correct. So then after a while, even the mathematics community starts getting interested to know what we're doing because they are barren of ideas. You see, in math, people all know what the questions to ask, okay, the $1 million Clay prize and all those Riemann hypotheses, but they are too difficult to solve. People know what are the open problems, they're too difficult to solve. So in the meantime, people still need to do some kind of research. And what they need are the questions. And so now, as a physicist, using our physical concepts in the context of string theory, giving them equalities, mathematical equalities that have never been seen before, implying new structures in mathematics, like, one side involving 4-dimensional kind of spaces, the other side involving 2-dimensional kind of spaces, one side involving geometry, one side involving algebra, the expressions, like a polynomial and then something else, okay, in an algebraic, in a geometric kind of quantity. It's something which they've never expected, and it's completely new for them, and it's a fertile source of conjectures for them to go and test and try out. And a lot of mathematicians in the past recent 20 years have built their careers on this, actually, on us providing them those things. And this is the whole third emerging discipline of string mathematics, which now at the String Mathematics Conference, you see mathematicians who are there to show us, the rest of the world, what are the things that are proven which were inspired from string physics. And then string physics people like me will go there and show them what are new things they can see. Okay, so this is what the string mathematics is all about. And it has influenced all these fields. Okay, so for example, just to show you how physical concepts can actually give rise to different topics, new topics in all the different types of mathematical topics like algebraic and differential geometry in this case. Okay, so for example, mirror symmetry of Calabi-Yau spaces. That's a new topic in mathematics, completely different branch of algebraic geometry, right? And simply the physics is because of this. Okay, so these are still abstract concepts. I mean, essentially, you have a string that's traveling in space-time. And on the worldsheet itself, because the strings are vibrating, you need to study a quantum field theory of the worldsheet to model its vibrations. And as with what I said earlier on, when you classically have a certain symmetry, okay, at the quantum level, you also ought to have that symmetry that's preserved. So this classical symmetry that you preserve at the quantum level, this symmetry that the string has, results in actually this thing. The 6 spaces that we saw it traveling in ought to come in pairs, that were in the past never expected by mathematicians to have these properties, the mirror properties. So essentially, the mirror property is that if you look at a Hodge dual of the Betti numbers of the Calabi-Yau spaces, they are mirror to each other. Okay, so anyway, that is just technical mathematical statement, but the point is, this case is simply symmetries of a quantum system, symmetries of a classical system going on to exist at a quantum system. Okay, that's the point of physics. Now the next one, this one here, quantum cohomology and Gromov-Witten invariance. So all these in dark are the mathematical topics that come about. So we have worldsheet instanton effects, okay, in topological string scattering. So you have strings that scatter, and then because strings themselves are not point particles, in the point particle theory of gauge fields, you have these things called instantons, but in string theory, you have worldsheet instantons, basically. Okay, so these are string worldsheets that actually wrap spheres that collapse to zero size. So in space-time, the string becomes a point. But the origin was that it was a worldsheet. Okay, so you study this, the scattering of strings, and then you can actually give rise to a new topic in mathematics called quantum cohomology and Gromov-Witten invariance. Okay, so this is also new. So same thing, then you have Donaldson-Thomas theory. I won't tell you much about it. The point is that all these dark ones are the new mathematical theory, and then you can study all these D-branes and the bound states. So D-branes are very heavy, right? We mentioned this now. So you can have D0 branes being bound to a D2, which is bound to a D6, and they are stationary and they are very heavy. Because they are very heavy, they will be very stable under phase transitions, okay? And then you can compute, basically, you can count them, and then you phase transition to a new state, and then you still count them, and then there's an equality in the counting. And then you end up getting like this kind of theory here. Okay, so mathematically. Again, because this D0, D2, D6 branes, mathematically, they can be expressed as some kind of sheaf over the algebraic variety, which is algebraic variety is the Calabi-Yau. Okay, so Calabi-Yau is called algebraic variety because you can write the geometry, or you can express the geometry of the Calabi-Yau as a polynomial equation in 4 complex variables. Just like if you look at a circle, x squared plus y squared equals r squared. That's the equation of a circle, but you have 2 real variables, x and y, in the polynomial equation that tells you it's a 1-dimensional circle. So Calabi-Yau is a 6-dimensional space. You can use 4 complex variables in the polynomial equation, and the locus will be a 6-dimensional space. Okay, never mind if you can't follow what I was saying. If you play this thing back, you'll know what I mean. Okay, so, and then generalized homological mirror symmetry. So you want to generalize this guy, then you have the branes inside, and then the branes will map to each other, and then you have what we call homological mirror symmetry in maths, which means that you have this phenomenon, but now objects inside, they map to different objects. Okay, so this is one possibility for algebraic geometry. So, and then non-commutative geometry. So the D-branes themselves, because they also have formally degrees of freedom, if you will, or matrix degrees of freedom, and then when you swap them around, the coordinates have a sign that they're non-commutative. Okay, so the coordinates, the positions are not commutative. You swap a D-brane around, you pick up a minus sign. Okay, so, and non-commutative geometry is also a new field in mathematics that was spawned out of the physics of D-branes. Okay, so very interesting. And then other things, okay, so, you know, I won't go through it because we are running short on time. But the takeaway is that you ought to be impressed by the far-reaching, you know, influence it has had on these different things in mathematics, all just by looking at all these things here. You see, they are all physics quantities. Okay, so anomaly cancellation is the cancelling of the d minus 10 equals to 0. So I think that anomaly is the quantity that makes a symmetry, that breaks a symmetry when you quantize a theory. Okay, so these are also physics concepts, and it gives rise to all these things in mathematics, new topics in mathematics. Okay, so yeah, even black holes, when you count the states of a black hole that account for its entropy, for example. Okay, and things associated with black hole radiation. Yeah, then you end up having automorphic forms in number theory. Okay, so, and then, you know, all these other things. Okay, so even the Riemann hypothesis, string scattering amplitudes also show evidence that the Riemann hypothesis is true, because there is an expression that they get which is ought to be correct, and we ought to be correct implies Riemann hypothesis about the zeta function. Okay, the straight lines, the zeta function that you plot, you know, the Riemann hypothesis tells you that there's this called the zeta function, and then the price must lie, you know, somewhere along the line. I can't remember the details, but that's a Riemann hypothesis. The most difficult problem in mathematics doesn't resolve it, but, you know, implied by string scattering amplitudes to be correct. Okay, and then just generalized Kac-Moody algebras coming out from strings. So BPS states are essentially the states of lowest energy, the most stable states that I talked about. Okay. And then heterotic strings I mentioned. Okay, so yeah, BPS again, you see the stable states are playing a lot of role in giving rise to new mathematics. Okay, just the stability of lowest energy states. That's like quite standard. You know, it's like a doll, right? Like, you know, if you learn the mechanics, you know, when the CG, when there's a stable equilibrium, that kind of thing. So this is essentially counting the space of stable equilibrium states. That's it. Okay, that will not be that will not topple or not, you know, not be thrown out of the regime when you have perturbations around it. That's it. It's a physical concept. Okay, but in the context of string theory. All right, and then you see some very crazy equations like that. Okay, so for example, if you look at this, again, this is actually just a path. It's a scattering amplitude. Okay, this is a path integral. The action is here. This is the measure of the path integral. Now, these guys that you insert inside are just strings. They represent the string states that come together and scatter. Okay, they represent string states that come together and scatter, and these equations are the classical equations of motion that the strings must obey. And in fact, in this scattering amplitude, a very special type of string, topological string, okay, they only take on the classical configurations, and you can actually very concretely determine that. Okay, so and then you have other things in string theory that just some mathematical equations to tell you how even knot theory, knots in strings, okay, you can also understand them through string theory. Okay, so and then toroidal algebras. Okay, bottom line is you get a lot of these equations that I flashed. They're all new from mathematics. Mathematicians have not seen this before. Like even
Prof. Tan, sorry to interrupt, but I think we all can't see the slides changing.
It's still blank at the title, string theory and algebraic differential geometry.
Yeah.
Oh, okay.
Yeah.
Why is it paused? That's kind of weird. Okay, let me try again.
Right.
Sorry,
sure.
yeah.
It's okay.
Okay, let me try again. Weird that it got paused now.
Yeah. All right, it works now.
Okay, so where did I stop here? Is it? This one, is it? Okay, anyway, when do I stop seeing the thing? This one you also?
I think it's this one, yeah.
Oh, here is it? Okay, anyway, so I continue from the earlier one where I showed you a lot of mathematics, and the point is that it's all derived from the physics of stable systems. Okay, it's physics of stable configurations. Okay, so and then you get all these equations from physics that are completely new in mathematics. Okay, so these are all new in mathematics. So you don't see this in mathematics. Okay, these are all new. Like this one is new, and all from studying the physics. And this one here is just energy conservation. Just energy conservation, counting the energy of the stable states. And then this one counts it in a certain way. This guy counts it in a certain way. Okay, because it's a dual theory. So this side here is algebraic in nature. This one is geometric in nature. So you get again a new kind of equivalence that mathematicians have never seen before. Okay, so this is how we connect geometry and algebra in algebra here and then geometry here. Okay, and here, this is a partition function that you all know for statistical mechanics. You're just counting the possible configurations, and you end up getting this kind of thing here that is an automorphic form. This is number theoretic in nature. Like this has got to do with number theory. Okay, so very interesting. You even have those very abstract things in mathematics coming out from the physics of string theory. Okay, and then more stuff. These are all new. These are things that mathematicians have never seen before. And for us, again, this is also another partition function. This is another partition function on the other side. That's it. Okay, we are partition function to partition function. That's it. Okay, so this is not really partition function. This is scattering amplitude. This is also a scattering amplitude. Okay, so you can see very sophisticated expressions which stem from very basic physical reasoning. So that's the power of this framework of string and M theory, whereby you just use very basic physical reasoning, but you can get very sophisticated expressions that mathematicians have never seen before. Okay, and then it's for them to just go and prove it. And because we have always been proven to be right, they are looking towards us for new inspiration, for new structures that we're discovering. Okay, so let me just end. Now, so string math, okay, the calculus of the future. So why is it called the calculus of the future? Clearly, we see a revival in the deep relationship between physics and mathematics, first seeded by Isaac Newton, who himself discovered the mathematics of calculus through an attempt to understand the physics of motion. Okay, so this has led to serious attempts by an increasing number of leading mathematicians to learn the physics of string theory. Prominent examples include Fields medalists like Maxim Kontsevich, Andrei Okunyukov, Xin Tongyao, and Pierre Delisle, among others. Okay, so they're all these top guys are trying to learn string theory because they're getting inspiration from us. So it is for this reason that string mathematics has recently been coined or dubbed the calculus of the future. Okay, and therefore its role in 21st century mathematics is actually this. Right? Now, the very interesting part, the emergence of space-time in string theory and the third revolution in geometry. So if you notice, right, all this time when we talked about string theory, we already assumed that the arena of events was already there. Even though we know that the closed string is the graviton, but that was to mediate the effects of the curvature of gravity. But then the arena itself was already there. X, Y, Z was already there. The axis was already there, right? So then the question is, how does the X, Y, Z axis even come about? How does the event, the space-time, even present itself? Flat or not, even if it's flat and nothing, how did it even come about in the first place? So this was the missing puzzle in string theory, because string theory assumes that X, Y, Z was already there, and then you work from there after that. Okay, even the expansion, I mean the nine circles were already there, right? So like, how did that guy even get there in the first place? So we are even more ambitious. We want to know why the space-time event was there. So we want to understand the emergence of space-time in string theory. And this leads to it will probably lead to the third revolution in geometry. So how does space-time emerge spontaneously? Okay, just come into being without itself. What is the mechanism for it to even be there in the first place? Now, in the context of this thing called the holographic ADS-CFT correspondence in string theory. So we discovered this correspondence in string theory, okay, between a space that's anti-de Sitter. So it's not really a realistic space, okay, because it has negative curvature. We know our universe has positive curvature because geodesics will converge. ADS is a space where geodesics will diverge, okay. So, but nonetheless, string theory tells us that if you study strings on a 5-dimensional space that's anti-de Sitter, at the boundary of this 5-dimensional space lives a quantum field theory. And why? Because the ends of the string again just end on the boundary, and so the boundary only got points. Okay, so the points will become a quantum field theory, and so that quantum field theory is a conformal quantum field theory, means it's scale invariant. Okay, and people have shown that if you study that quantum field theory on the boundary and study the entanglement of the quantum states of that boundary, then what happens is that equivalently in the 5-dimensional space with the extra dimension, where there is gravity, because the gravity is made up of the closed strings, okay, not points, there will be a space-time kind of trope that forms. So people see that there's this connection between entanglement of quantum states and the formation of a space-time bridge. So how space-time emerges spontaneously, is in some sense related in this context to quantum entanglement. Okay, so then people started getting very interested in quantum entanglement because they believe that quantum entanglement would then probably be the origins of how the XYZ axis comes about. Okay, and I'm not sure whether this is right yet, because ultimately this is still discovered in the context of a space that's negatively curved, okay, and a lot of other things which are not exactly realistic, okay, but nonetheless it points to the suggestion that we ought to see these things, quantum information and quantum entanglement, in a different light. Its use, it could really be that the XYZ axis springs up from quantum entanglement and quantum information. So this suggests that quantum information theory is intimately related to the emergence of space-time. Now, do I think this is correct? My personal opinion is that it might be, because if you look at XYZ, okay, the axis, that's information, right? That is like XYZ is information. So the metric, the space-time, by specifying a space-time, you're specifying information. You're specifying how many directions, you're specifying, how is the geometry or direction, you're specifying information. So in this way, you can see that information is actually even more fundamental than geometry, right? So let's say you have a metric, in geometry. A metric tells you how, how to evaluate the lengths of vectors, okay? And that depends on the metric, right? So the metric is made up of, it's a matrix, with different components inside, and the components themselves are also pieces of information. So you can see that actually, from this point of view, that information is indeed more fundamental than geometry. Okay, so it could be that there will be a third revolution in geometry. Third in the sense that the first was Euclidean, of course, Euclid, okay, where he defined X, Y, and Z, the flat one. Okay, so we understand, and then Cartesian coordinates and all those things. Okay, then came people like Gauss and Riemann, who decided to study curved geometry. Okay, started to study triangles on the curved surface, for example, right? And that was the second revolution. So from flat geometry to curved geometry and Riemannian geometry, and then maybe the third revolution in geometry is the following: that before you even define geometry as it is, the metric and the lengths that the vectors can be evaluated over and all that, the geometry itself, the idea, the mathematical framework of geometry may have an axiomatic information theoretic origin. That means you have axioms first to say, okay, like the metric is this, but before that, the entries of metric are dependent on this information. Okay, so information is even more fundamental than the very construct of a geometrical theory. You see my point? So it could be that there would be a third revolution in geometry as suggested by this thing, whereby geometers themselves start studying axioms that allow them to construct the ingredients of geometry, i.e. the metric first. The very first thing is the metric. Later on, they can construct other things. The Riemann curvature, if there's any curvature, Riemann 2 tensor, whatever, scalar, whatever, all those things. All the things in geometry stemming from the metric first. But before the metric, maybe there could be an information theoretic, axiomatic way of defining the metric. Okay, so I believe that that could be true. And again, you can see, it comes from something that we saw in string theory. So string theory is feeding back into itself to tell you how we should even think of X, Y, and Z and how it came about. Okay, so that's the beauty of string theory. Even though it has not, even as we understand it, we have not solved or understood the underlying reason why, in the first place, its starting point is here. From a later part, it's telling you the starting point could be like this. Okay, it's feeding back onto itself. Okay, that's the beauty of string theory. That's a wonderful, wonderful gift. It's a gift to humanity, where it's from, this ultimate science. It's a gift. Okay, it really is a treasure trove of many, many things. I've only skimmed the surface of what you can do. String theory also has implications for people who are studying condensed matter. Graphenes also, there are. People are studying graphenes, strongly coupled quantum field theory systems. They make use of ADS CFT to compute things. So the graphenes will be like this part of the correspondence. And then if the coupling is very strong, the ADS CFT tells you that the computation here involves a weak coupling. So you can use perturbation theory and string theory to compute the thing here, then feed back to the answer here. And people are using this. So even if they didn't use string theory to understand the theory of everything, they are using string theory to understand things in normal physics. Same thing with Fermi liquids, okay, topological insulators, same thing. They all are on this side. And then if the coupling is strong, they can't compute, then they use this side. And then they get the answers. So even if it's not involving things which are related to string theory and the theory of everything, string theory itself is able to help. And so in ending this thing, I will say this, so there could be a third revolution of geometry, as implied by string theory even. And there could also, and string theory must be understood in the following sense. Okay, it must be understood in the following sense. Just like quantum field theory, it should not be interpreted as one single theory. It should be interpreted as a framework. So quantum field theory, even though it's called quantum field theory, we all know today that it is actually a framework. In what sense? Let's say in quantum field theory, in the cookbook of quantum field theory, you have the Klein-Gordon scalar boson, scalar field. You have the Dirac fermion, for example. You have the gauge fields. And then depending on what kind of experiments you want to describe, let's say you want a graphene that is only moving in 2 dimensions, but with some potential, some field that is affecting how the electrons are moving, then you construct a Lagrangian of the graphene theory using Dirac fermions, for example, in 2 dimensions, adding a gauge field in 2 dimensions, and there's some potential of a scalar field somewhere. And then you can construct a Lagrangian that describes the graphene system, for example. Okay, or like Fermi liquids, or anything of topological insulators, 3 dimensions, 4 dimensions, 2 dimensions, 1 dimension also can. 1 dimension, even if you're talking about electrons are flowing in 1 dimension, you can still write a Lagrangian that's 1 dimensional for it, okay, with a potential that's affecting its motion. And if you notice all that I've said, we're using parts of the quantum field theory cookbook to construct a Lagrangian to describe those different things. So quantum field theory is not a theory. It is a cookbook. It is a framework from which you can construct your own theories using its building blocks to model what you want. Now, string theory, even though it was supposed to be a single theory that was meant to describe everything, if you look at it now, it is again just a quantum field theory where it's a cookbook also. It's more than a cookbook. It's got its separate building blocks, like ADS CFT is one sub-concept. It can even be used for other things, not just to construct a theory, but to have insights into other things. And then, I think one day, my hypothesis is that when we finally understand string theory fully, we would be able to utilize it like how we utilize quantum field theory as a cookbook whereby we construct a particular type of string theory from the 5 different string theories and their subsets to describe one, to use one to describe the universe that we are in. Okay, and how do we know that this is definitely correct? So if you look at quantum field theory, every quantum field theory, special relativity is embedded in it. Okay, so that's why when you start taking building blocks of quantum field theory to construct a Lagrangian to describe a system, you can always use that to describe a system whereby the electrons are moving at fractions of the speed of light, because that's when it's relativistic. and you need a quantum relativistic theory. And every quantum field theory, the building blocks, the time-Gordon boson, the Dirac fermion, the Young-Mills field strength, inside special relativity, the mesh shell condition, which encodes special relativity, is really inbuilt inside. So special relativity is part and parcel of every building block of quantum field theory. Now you look at string theory, graviton is part and parcel of every string theory. It's inside. So quantum gravity is really inside every sub-string theory, every different string theory. So we can tell that if we want a theory of everything, of the graviton and all the force fields inside, then the building blocks must come from string theory. So this is how the world should see string theory. And sometimes you go out there and you look at people who there are some very anti-string sentiments simply because people are impatient. They don't want to wait for another 40 years to find this evidences that string theory is right. So it's a sociological reason. People are fed up with it. They are not patient anymore. They say that you promise that this would be a theory that tells you everything, but we still aren't able to prove it yet. I would say it's only because we have only now come to discover or understand that it is not one single theory, but it is rather a framework, a body of knowledge, whereby we have still yet to be able to understand how to piece the building blocks together to create or write a Lagrangian, let's say like the standard model, to describe the quantum forces of the atom. The standard model is a Lagrangian that's made up of the Dirac fermion, the Young-Mills photon, the Young-Mills gauge fields, and the Higgs boson, the scalars and all that, put in a certain way such that they'll describe the standard model. So the same kind of thing, quantum gravity theory, a theory of everything for our universe, is a certain construct. But string theory is much more than that. Okay, and that's why it's giving you all the new mathematics. And it's even suggesting a third revolution in geometry. Okay, so this is the takeaway. All right, it is not just a single theory, just like quantum field theory, it is a framework, it's a toolbox. But we are not there yet to understand how to construct, string theories like in the way we are able to construct quantum field theories. We are not there yet. So there's work to be done. We understand quantum field theory much better. Okay, so but it will go along the same lines. Okay, so in case you were lost along the way, let's summarize. String theory is a leading candidate for the theory of everything in physics, and why we know it's the right building blocks for that, because graviton, quantum gravity is inbuilt into it, just like special relativity is inbuilt into quantum field theory. Okay, it's in there already by default. So string theory remains to be fully understood, as I mentioned. Due to technological limitations, string theory has not been experimentally verified to any extent yet, but that does not mean we should give up on it. Okay, and string theory is also a source of inspiration ideas in current and future mathematics. In particular, it even suggests a third revolution for geometry. Okay, and so thank you very much. I hope you enjoyed the talk. I far exceeded the time, but I feel compelled to tell you everything about it, and that's why I've taken this long. Thank you very much for your attention. I hope you enjoyed it.
Right. Thank you, Prof Tan. Thank you very much. Thank you for the very in-depth and thorough discussion on string theory and its role in 21st century mathematics. It's very interesting. And I think it is now appropriate for us to proceed to the Q&A session, shall we?
Sure.
Right. So,
I mean, you can just ask me anything. I mean, don't feel shy. If you don't want to show your face, I think if you ask me in person, better than typing. Typing is a bit tedious. So, you just ask me. Yeah. You just ask me. Yeah. Yeah, you don't have to show me your face. You can just unmute yourself and then you can talk. Yeah.
okay.
You can chat.
Can you all see the screen? Or no, you guys can't see anything. Oh yeah, can really. Okay.
Okay.
Right. So we have I would say about more or less 10 questions here. So I think I'll read out. Right. Let's start with the first one. It says, Professor, since the universe can be explained by a single unified theory made up of mathematics and equations, is it possible that this universe is just a simulation of a supercomputer by another universe? If so, could that universe that simulate our universe itself is also a simulation by other universes?
Okay, so you see, as I mentioned, string theory is a framework. Okay, there will be a single sort of theory constructed from the basic building blocks of string theory to describe our universe. That is what we are all hoping that we can do. Okay, and most likely that is going to be the case. Okay, just like the standard model is a particular Lagrangian made up of certain building blocks of quantum field theory. Okay, so in the quantum field theory book, right? And so is made, so it says it's made out of mathematics. Okay, mathematics is the language for physics, but it is not physics. Okay, so what I'm trying to say is that a mathematician is unlikely unless it is sheer coincidence. Okay, it's unlikely that a mathematician can actually discover an equation that will describe our universe just purely on mathematical grounds. Okay, it's unlikely. Okay, because mathematics is just the language of physics. It is not physics. So an analogy is this: you think of mathematics as a dictionary of words. So mathematicians, when they come up with new kind of theories in mathematics, discover new things, it's like they are inventing new words. And then physics is the story. We take their words, put them together and tell the story. Yeah, so that is the analogy. So a dictionary cannot tell the story. Dictionary can only supply the words and the, so-called the vocabulary for you to express your story, your idea. Okay, so in that sense, if you're talking about the universe being a simulation of a supercomputer, well, supercomputer works on logic and therefore is closer to mathematics. Physics, the story itself depends a lot on intuition. For example, let's say if you look at GR, the fundamental principle of relativity, general theory of relativity, is the principle of equivalence, whereby acceleration and gravity are equivalent. There is no mathematical way to write that. It's an intuition. So, you could write Einstein's equations, A pi g equals to t, that you can write as a mathematical equation, a 4x4 matrix equals to a 4x4 matrix, for example. But there's no way to write the equivalence principle in mathematics. There isn't. Okay, so in that sense, the physical universe that we know, requires intuitive input to understand and even to realize. And if it's just a supercomputer that is, based on a logical way of doing things, much like mathematics, in my opinion, it can't be simulated by a supercomputer. Okay, in fact, my view is the following. My view is that the universe as we see it today, right? Okay, emerges out of environmental reasons. Okay, what I mean by that is this: you look at the solar system, the distance between the Earth and the Moon, for example, or between the planets, that cannot be described. It just happened to be this way because it came about from the chaos of the Big Bang. We can describe the motion as in through the centripetal acceleration of the planets around the sun, that we can describe. But the default distance that came with it, okay, that we can't describe. Okay, and I don't think any fundamental theory would also be able to describe that. Okay, so in string theory, we are attempting to even come up with the mass of electron, mass of the charge, and all those things, those constants which we see. It could very well be that even these values are environmental in the sense that they spring out of the chaos, of creation to have these values only. And it is also therefore okay that we do not have, derivation of, say, the distance from Earth to the Moon, for example. Okay, that's fine. We accept it as it is. It's more important we know how the Moon and the Earth go around the sun. That's more important, the dynamics of it, basically. And that in string theory, in fact, all the things we kind of know already. The remaining things that we still don't know yet, that leaves, leaves people to criticize it and not be able to come in contact with the universe, is because these things, these very fine-tuned values of things, we are still not able to derive that from first principles. But it could be that these are environmental. In fact, there is this thing called the landscape in string theory, whereby people who study how string theory gives rise to the observable universe, they realize that there are multiple solutions, possible solutions to a universe that can contain life, basically. The missing thing which they still cannot figure out is why some of these values are so fine-tuned. We still don't have a first principles derivation of, say, the charge or electron or something like this. Okay, right? Those things. And then, some people propose that just like the distance of the Earth from the moon and all those things, which are environmental in nature, okay, these things are similarly environmental in nature. So some people accept this to be correct. I personally accept this to be correct, okay, and some people think it's a cop-out because, you know, ultimate theory should be able to describe everything. Then if that was the case, I would also say then that an ultimate theory should also describe and explain why the distance between the Earth and the Moon is this. But I don't think we can ever explain that. Okay, it just happens to come about from the whole chaos of the universe, you know, developing and all that, right? Some things are just that. And it's actually fundamentally more important to know the dynamics of the things, the interactions and how they will be, than the actual value of certain things itself. Okay, so anyway, I digress from that question. So the simulation by a supercomputer would mean that everything is down to basically, you know, hard facts and logic, but there are many things in the physical world that possibly may be environmental in nature, in its values, and may always and forever lack fundamental reason why it is such, like the distance of the Earth, you know, from the Moon, for example, that kind of thing. Okay, so that won't be simulated by a supercomputer then, if that's the case. Okay, so as I understand the supercomputer to be one which, you know, is based purely on logic and very concrete values of things. Okay, right.
All right, moving on to the next question. It says, hi, Professor, what advice would you give to those who are interested in doing theoretical physics in the future?
I think first and foremost, it's important to get your fundamentals strong. Okay, don't be impatient, especially in the 21st century. This is an attribute that cannot be overstated. Okay, why I say that? Okay, so you must be patient to know many things. The definition of a genius today is very different from, say, back in Einstein's time or Schrodinger's time or Heisenberg's time. Okay, back in those days, they only needed to know one thing very deeply. Einstein could just reject quantum mechanics and still be Einstein. Okay, he's still Einstein because he discovered the principle of equivalence and relativity, right? So he just needed to know this, think about this, and didn't have to care about what Heisenberg and those people are doing in the matrix and all that. Okay, doesn't matter. He's still Einstein. The matrix people were the same. Okay, Dirac and all those people, they didn't have to care what Einstein was doing, and they were still, you know, the quantum mechanics people, right? And the quantum field theory people in the 40s and 50s in America, especially the particle physicists, didn't have to care about the black holes, and they were fine. Okay, they were okay. And Hawking and all those people just cared about black holes, and they were fine also. They were also okay. They were still Hawking and all those people. But today, all the fundamental pillars of physics are more or less established. So like the quantum field theory is one fundamental pillar, relativity is one fundamental pillar. So the next stage of discovery is essentially unification. That means finding the connections between all these different things that our predecessors and our academic ancestors have discovered. So to do that, you require a broad base of knowledge. The knowledge is even more important than the depth first. So you may not have the depth, you know, in understanding every single thing, but it's more important that you have an idea of all these things first. Then you will know where the connections are to be made. So the definition of a genius today is very different from the old days. The old days was a very deep thinker. But today, the definition of genius would be, say, for example, someone like Witten. The reason why he's Albert Witten is because he knows many, many things. So he's a monster mind that is an encyclopedic mind that knows many, many things. And every time he's able to make a research discovery, it's because he's able to unify and marry different concepts that he saw were disparate, you know, and then he was able to link them and then make the next breakthrough. So the requirements are that you need to be able to know a lot, have a lot of knowledge, and then from there see the connections and then link them. Not so much thinking of one fundamental way of, you know, making a breakthrough in something, because the fundamental thinking has been done by Einstein and the quantum mechanics people and the quantum field theory people. That's done really, basically. The next fundamental thinking that people are doing right now, I would say, mainly is trying to link information to the emergence of space-time. That's something fundamental that people are thinking of now, okay? And many people are trying to think about that. But I would say even if we figure it out, if we figure out information theory and its emergence of space-time, we still have to put this in the context of our quantum field theory and our GR and those other things that we really know, and I don't know whether you will fit nicely after that, because we're just talking about information and gravity. That's it. We're not talking about gauge fields, which are the photon. Those things are still present in our everyday lives, and so we still don't know about that yet, whether that kind of, even if you know the connection between information theory and the emergence of space-time, how does the gauge field and all that interact with the information theory and all that we still don't know yet. So it's still a long way to go. Okay, so people are thinking about something fundamental, but I think even then you cannot avoid after that having to integrate the rest of the things. Okay, so the point is going to be patient, get your fundamentals right, be curious about everything. Okay, obviously it's just natural for people to like some topics more than others. I mean, even though you love physics, there are some topics that you like more, some topics that you don't like as much. But in the grand scheme of things, if you really want to be successful in doing this, then you have to be ambitious even with what you know. That means you must have this, even with some topics that you don't exactly like, you must kind of, sort of encourage or force yourself to learn it well, for example, right? Then, you will in the bigger goal of knowing everything well. And then that's how that's the, the advice I will give you. Okay, be patient, get your fundamentals right, persevere, okay, persevere not just academically, but, psychologically, psychologically, you got to persevere. So this is always remember that, this is the ultimate thing. And if you want to do the ultimate thing, there will be an ultimate price. Okay, so no good thing comes free. Okay, so that's the advice I will give you, right?
All right, that's a very good answer.
Yeah.
All right, so next one. I think I should go with the top one first. What are the required mathematics one must study if one is interested in string theory?
Okay, so there's one book that I recommend that if you understand that book, you'll be fine. Okay, so it's called Geometry, Topology, and Physics by Nakahara. Okay, and if you read that book is actually written by a physicist. Nakahara is a physicist who puts in this book all the mathematics that you will need for the different types of physics involved in string theory and quantum field theory. So that book is very good in the sense that there will be an introduction chapter that shows you all the problems, or rather gives you a sample of problems that you would see in quantum field theory and string theory, and the kind of mathematics that's involved. Okay, that was the introduction. Then the main body will teach you the mathematics, the concepts of these mathematics. Like for example, let's say, in anomaly cancellation, string theory, okay? So you need to learn some index theorem, that kind of thing. So the first part of the book will show you a calculation regarding anomaly cancellation in physics, a path integral and all that. Then it shows you that, okay, in order for you to compute this thing, you need to know to use this formula. This formula is in the topic of index theorems, for example. Then it will, in the main body, chapter 7 or 8, you'll go into index theorem. So it will do this. That's why it's very good for a physicist. It gives you the motivation of why you need to study the mathematics, and then it will teach you the mathematics that you need. So that book, if you finish that book, if you master that book, that's all you need to know for mathematics or string theory. Then later on, when you actually do research, as you do research, because it's cutting edge kind of stuff, then you need to learn like specifically some types of mathematics beyond that book, but not everything. So let's say if you work on black hole states counting, and then you encounter these things called automorphic forms in your expressions. That's in the realm of number theory that Nakahara doesn't teach. Okay, and then you must then go and read up some books on automorphic forms on your own, but that's just specific to your research. So every research paper is also a chance for us to learn something new. So doing this thing, you are a scholar in the truest sense of the word, that we are just doing nothing but studying our whole lives, like learning new things, learning how we ourselves are learning. Okay, and so to be a good physicist, at least what I have observed and learned from Witten is that, you see, he can treat every paper that he has worked on like a thesis. most of us only have the endurance or even the passion, if you will, to work on our PhD thesis like a thesis. And usually a lot of people do very well for their PhD thesis because that's the thing that they are going to write, do for their PhD. But as a researcher, if you think about it, right, I've had like maybe 7 students by now, and each of them writes about 3 papers for their thesis. I mean, as a researcher, we are just writing PhD thesis after PhD thesis because we just have papers after papers after papers, right? And then 2 papers or 3 papers usually make up 1 PhD thesis that we give our students, but we ourselves are just churning paper after paper after paper. If you are qualified to be a professional researcher, it will mean that you can constantly just come up with papers, ideas for papers. Now, so the difference between a very successful researcher, someone who can go very, very, have far-reaching results, is one whereby a researcher, someone like Witten, who is able to regard every project like a thesis, take it seriously like a thesis. Okay, so if you can do that, then you can succeed in being a theoretical physicist. Okay, so that is the thing, so the sort of the mentality that people should have. Okay, so the person who can always regard every paper that he or she writes, the new paper as a new thesis, then you will do very well. Okay, yeah. What else?
Okay.
Okay.
So the next question. All right. It says, can I have your advice and opinion if someone wants to further their study or research on string theory or research that is related to quantum theory, either theoretical physics or experimental physics? And the follow-up question is that what is the I think you say that what organizations or universities are out there that we can enroll in to further the research and also the study?
I mean, okay, so can I have your advice and opinion if someone wants to further their study or research on string theory? So same overlapping advice, which is get your fundamentals strong first. Okay, definitely try your very best to get your fundamentals strong. I will say the following: if you want to be a theoretical physicist, then getting good grades is important. If you want to be an experimental physicist, then I would say it's not as important. Because in experimental physics, I mean, you need to be good with your hands. You need to have some, of course, background in the physical theories, but it's probably even more important to be good with your hands. Okay, so then just being academically strong is, of course, always preferred. But if you can't, it doesn't mean it's the end of the world. You can still end up being an experimental physicist and discovering something, even though academically you may not be as strong. Okay, so, but as a theorist, I mean, one of the pre-requirements is that you must be academically strong, because what are you doing? You're just doing academic research. So you've got to be academically strong. But that being said, being academically strong is not the be-all and all. Because as a researcher, when you're academically strong, it only means that when given a question, like an exam, you can solve it. So you're a good calculator, that's what it means. So if you've got very good exam grades, you're a good calculator. But as a researcher, what you want to be able to do is to ask a question that is hard enough to be interesting, such that nobody has done before because it's hard, but yet easy enough to solve. You must have the knack of sniffing out or coming up with questions that are hard enough to be interesting, but easy enough to solve, so you can write a paper and solve it. Now, that has got nothing to do with the academic grades. Okay, that has got to do with, that is the talent we're talking about in research. So some people have more of this talent, some people have less, but certainly it's not a talent whereby if you have less, then you can't hone the talent. You can hone the talent by essentially reading more, okay, by following more, like, how people in research think. You can mimic that basically. So you can look at your supervisor and how they think and all that, and get involved in the process of how people come up with research questions, and then you can learn the way of thinking. Okay, so the point is that good grades are a requirement for a theorist, but they are not the only thing. The ability to make connections, that's also important. And usually that involves, again, a broad-based knowledge, because the broader you know, the higher probability of making a connection. And then that will be a new question. Okay, so that's the point. The broader you know, the more probably high probability you can make a connection. Okay, and also having a sense of creativity, like you got to be a bit creative and not just imaginative. Not creative is not the right word, but imaginative. Okay, so equivalence principle was born out of pure imagination. If you think about it, the equivalence between acceleration and gravity and the leaf falling and then the free fall and all those things. That's pure thought, basically, pure imagination. So you also kind of need that as a researcher today to have some creativity with certain things and imagination with certain things to link the things together. Okay, so I would say, yeah, you're going to further your study on research on string theory. You have to first and foremost do well in your grades. You know, get our fundamentals right. Okay, theoretical physicists, very important. Experimental, you should also try, but in the event that you feel that your grades aren't as good as you hope to have, but you still want to do experimental physics, I say go for it, because if you're good with your hands, you can still make new discoveries. Okay, and the truth of the matter is that, you know, neither is more important than the other. Like experimental also important, because at the end of the day you need things to work for to contribute realistically to the world, right? I mean, you can do all the theories in the world and then nothing materializes, is equivalent to nothing also, right, in a way. So if you do experiments, you know, things work, you can, you know, push it out to have a new technology and all that. And so that is actually crucial. Okay, so neither theory nor experiment is, you know, more important than the other. Each have their role to play and both are equally as important. So organization or university that you can enroll in to further our study and research, I mean, depends on a few things. I mean, if you want to stay in Malaysia, I don't know. I'm not sure. I'm not sure in UM or here you all have this. I don't know. I don't know the system. But Singapore definitely. I mean, you have people who work on this. I mean, I work on string theory. Okay. In NTU, is there maybe there are some people working on quantum field theory in NTU. Okay. Here we definitely have in NUS string theory. You have people want to work on gravity, you have. You want to work on quantum information, you have. So I would say you can come to NUS if you want to study a PhD in all these things. Theory stuff, then you can come to NUS. Yeah, not necessarily just string theory, other things, other theoretical stuff. We have people who are working in quantum information. There's a quantum computation, quantum center here, quantum information center here. Okay, and some of the people in quantum information center are working on trying to figure out how gravity comes about now, because of the quantum information thing. Okay, so I've not talked to them yet because I'm working on string mathematics, so my focus is not on this, but I'm also curious to know whether quantum information can result in emergence of gravity. Yeah. Okay, so that answers the second part of the question, I guess, right? Yeah.
Yeah. All right. So there's one more on the right. He or she asked that, can the speed of light? Wait a minute. What's that? Is the speed of light is also known as the speed of causality? If so, and why it is?
I don't really understand the question, the speed of causality. Yeah. Causality is just a concept that if you know, something arises from a pre-event, you know. So yeah. So from an English point of view, yeah, you can say so, because let's say if an event happens here and it needs to communicate to something else before the next event can happen, the cause next event, then the speed of that causal consequence is the speed of light. I mean, it could be slower than that, but the fastest is the speed of light. So the speed of causality, the limit of the speed of the causal event, you know, process is the speed of light. Yeah, so you could say yes.
Okay. All right. So now we have one down there. Yeah.
Okay, sure.
What do you think is next for theoretical physics after we solve the theory of, I think it's after we find a theory of everything. And what do you think is next for our understanding of physics?
You see, the theory of everything, once we have the correct construction of the right string theory to describe our universe, okay, the unification of the four forces of the universe, then as I mentioned in the whole lecture, you study string theory generally, it gives you all these new mathematics. So the theoretical physics can now feed back to mathematics and grow mathematics. Okay, so it doesn't end there. So string theory is a body of knowledge. You know, it's like a treasure trove of knowledge, basically, not information, knowledge. of mathematical and scientific knowledge. Okay. So after you solve the theory of everything, which means constructing the right string theory to put together to solve that, there are more things that you can do. And if you look at, even if we solve the theory of everything, get the right string theory that describes everything, I mean, there are many things in physics that still needs to be understood independent of string theory. Okay, because you said theoretical physics, right? So theoretical physics got many things. What we're doing in string theory is actually high energy theoretical physics. There are people who are on superconductors. Let's say you want to find some material of high temperature superconductor, and then there's some theoretical models for that. That's also theoretical physics. So theoretical physics is actually a very broad subject. Anything that involves theorizing about some theory, could be on insulators, could be on superconductors, could be on graphenes, could be on new materials, as long as you're not working in the lab on it, but proposing some kind of theoretical construct, usually using quantum field theory to say, then you're also theoretical physics actually. Okay, so there are people who do that. Quantum chaos, for example. There are people who study chaos systems at the quantum level. So there's still a lot of other things that can be done independent of the theory of everything. The theory of everything just wants to find a framework that will allow us to understand the Big Bang, basically. So the four forces unified together, what will happen, the origins, basically, of our existence. It serves to explain that. But that theory of everything will not be able to describe for you, say, quantum chaos, which is a different thing, or thermodynamics and some other thing which requires more macroscopic or more ensemble kind of understanding. Okay, so that's the thing about physics. The theory of everything itself, although unifies all the four forces, there are sub-branches of phenomena which need their own kind of description. So this is also true in all of science. Say physics, quantum mechanics, we describe the atom. And then molecular physics, okay, we describe the molecules. Okay, so quantum physics to atomic physics to molecular physics. Then comes chemistry. So chemistry, if we were to go down to Schrodinger's equation to solve the molecular structure of, say, amino acid, like you go mad, man. It's so complicated. This amino acid, hydrogen, carbon, and rings and all those things, right? In organic chemistry, it's impossible, and you don't need to use Schrodinger's equation to actually solve that. Basically, you need to understand it from a different macroscopic ensemble perspective of things, and you can still get very accurate results. So within theoretical physics, there's also such phenomena where the most fundamental theory that you get need not be used or shouldn't be used to even study other phenomena which you can see from an ensemble perspective, a more macroscopic kind of perspective. You understand what I mean? So there are still more things to be done. Okay, and if you talk about purely in the realm of string theory, once we discover the theory of everything, what else is there to be done? Well, the implications of the mathematical implications of string theory, that is still ongoing. It's ongoing now. It will continue. In fact, I just finished chairing a conference on M theory. Okay, and there are new things coming out from the physics of M theory, much more sophisticated stuff, higher categorical theory of in mathematics, the new kind of group theory in mathematics. It's something that it's like a higher group theory, if you will. Okay, it's a new stuff that people are working on. Okay, so and that will continue. That will always be alive and continue. Yeah.
Okay. So there's a question that what is the relationship between quantum field theory and string theory? And what do you think will be the future of quantum field theory and string theory? I think this is more or less similar, right?
Yeah, okay. So quantum field theory and string theory. See, so quantum field theory is a theory of point particles.
Yeah.
So the string, when seen from far, is a point particle. So quantum field theory is the macroscopic distance theory of the far range distance theory of string theory. Okay, so every particle that you saw, the electron, the quarks we saw, they were composites of all the strings. Then when you see from very far away, they're like points. And the quantum field theory describes the quarks and the electrons and all those things. So basically, quantum field theory is a long distance approximation or magnification of string theory. So that is the relationship. Okay, of course, there are many different types of quantum field theory. It's again a cookbook. quantum field theory is not a theory, it's a cookbook, but so is string theory. It's also a cookbook, okay, of things. Just that we have not learned how to utilize this cookbook and its building blocks as well as we are able to do with quantum field theory yet. Because our techniques of working with point particles, we are much more familiar. We're working on strings, there are some things which are not so familiar yet. Partly it's because, I think it's due to the mathematical tools that we have. If you look at points, if you look at calculus, dy, dx, and all those things, we are breaking down functions into, the evaluated at points, for example. So points we know how to do very well. If you start having functions that are valued not at points but at like circles, like a string function, for example, then what is the dy dx for that? We are not sure yet, actually. That's the reason. So you see, if everything is based on points, we know what to do. That one we know. Mathematically, we have the tools. The calculus, we know what to do. But we don't have a string calculus yet. What if the smallest entity of a function takes values over a loop, or takes values over an open line and not a point? How do we differentiate these kind of things, for example, or integrate? That we don't know yet. We don't know how to do properly yet. And maybe that is the reason why we are also unable to find a way to mix and match string theory in the way we can do quantum field theory, because ultimately the mathematics ends up being calculus in nature, basically. Yeah, so that's the thing. Okay, so what will be the future of quantum field theory and string theory? Well, it will give rise to all these things that we mentioned. From string theory, there will be new mathematics. Quantum field theory, in fact, quantum field theory alone, without going to string theory, also gives us new mathematics, really. They are also giving us new mathematics. In fact, regular quantum field theory without supersymmetry, people are studying defects in it. Defects are objects that are not points, but like could be a line, could be a two-dimensional wall or three-dimensional boundary. Defects in quantum field theory, and then they are starting to see that when you have such defects in a quantum field theory, they are related to higher groups. Higher groups is again a new kind of mathematics, so people are investigating that. Okay, so there are a lot of things to do. Quantum field theory, as much as we think we know it very well, there are still some things that we don't know very well about quantum field theory. That's why it's very hard to find a good book on quantum field theory. It's very hard to find. Quantum mechanics, you can find some textbooks which are very good already. GR, you also can find textbooks which are very good. But QFT, sometimes you want to study QFT, you read this, like, okay, it's all right, but it's missing something. Then you read the other one, it's all right, but you're missing something. So no one has really written a very good book on QFT. And this is indicative of the fact that people still don't know it as well as we should. Okay. I would say probably there are better books in string theory, okay, than QFT. Maybe because I think string theory as a structure is more elegant. Okay, doesn't have all these infinities that you need to renormalize, and it's just an elegant theory, basically. QFT is a practical theory. It's a very useful theory. It's something that we can learn quite quickly, because it's just an extension of quantum mechanics. But I think because there are things that is something not so right about it yet, then we can't really understand it fully also, because the structure is a bit, still somewhat haphazard. Yeah, so that's the thing about QFT. Yeah.
Right.
So what's next?
Okay, Prof Tan, do you think, is it okay for you that if we pick just one more question and then
Sure.
I think the rest I'll let them email you, or is that okay? Is it fine for you?
Yeah, email me. Yeah, I think we've got it for a bit too long, right? So yeah.
All right, I'll pick one more. Let's see
Yes.
which one is interesting. Okay. I think there's
How about
this
that one?
one.
Okay.
Yeah,
Which one?
Yes. Which one do you?
Okay, how about let me pick one.
Right.
I want to pick a difficult question. Yeah. So
go.
I want to address it. Let me see.
Yeah, sure.
Okay, I'll pick two. Okay, because I think these two are things I want to answer. Hello, Prof. Is it true that string theory has a huge number of vacuum states? Okay, I mentioned this about the string landscape just now, right? Of the multiple number of possible universes that string theory predicts. Okay, If so, does this affect the theory's prediction ability? Okay, so my view of it is the following. Remember, I talked about the environmental factors that determine the distance of the Earth from the Moon, for example. Okay, so what's happening with string theory is the following. We set out to find a theory that would give us, the mass and the charge and all those things from first principles. We set out to do that. And in fact, we have already modeled a theory of strings whereby the vibrations and all that ought to give you these things. But so far, I won't say that in future it's going to be like that. So far, we have failed to find a mechanism that will compel us to say that the mass or the charge of electron should be such. Okay, there's no more fundamental reason that compels us to do that. And instead, contrary to what we expected, we ended up getting, possible solutions, many possible solutions, to string theory. Okay. And so, as I mentioned in the talk, some people say that this is the failure of the theory. Okay. Some people say that this is something that we just accept that, just like the distance of the Moon to the Earth, ultimately why the charge of electron and the mass and all these things are so fine-tuned in this way is basically an environmental factor, and that our existence, you see, our existence depends on the formation of water and all the fine-tuning of these constants. If one was just off a little bit, then there will not be life in this universe, for example, life as we know it ourselves. Okay, so then some people will say that, yeah, okay, so we need to use entropic principle to explain this, which means that it is through the permutation, all possible permutations, that an order comes out from it. Okay, that's like the entropic principle. Okay, so that these values for the electrons, charge and mass and all these things are environmental. Okay, okay, and that there is no further sort of explanation for that. So I tend to think that this could be true. Okay, because we didn't set to look for infinite number of solutions or 10 to the power of 500. It's not something but we are guided towards that. And why we should trust that this is true? Because if string theory were completely wrong, why should it have so many connections with a rigorous discipline like mathematics? You see, it is producing for you formulas which are verified using completely different methods that are exact. Why should it be wrong then? Why should something that is wrong, at least in terms of a piece of knowledge, if a piece of knowledge is fallacious, is wrong, why should it give you results whereby mathematicians, where they compute exactly in a different way, also can verify that your results are right? It's a Pythagoras theorem of a right angle triangle. Hypotenuse squared equals to side square plus side square. So mathematicians have a way of proving it. So in string theory, we are like getting hypotenuse squared as one part of the energy. Then the other squared plus the other squared is another part of energy, and they are equal to be the same. So if this theory was wrong, there's an untruth in it, why should it reproduce a formula that was proven to be correct exactly, basically? So that's the thing which tells me. So to me, mathematics is a lab for string theory, because mathematics itself is an independent truth. And it's a Platonic truth in the sense that Pythagoras theorem, 2000 years ago, it was discovered to be true. 10,000 years later, it will still be true. Nothing will shake the truth of Pythagoras theorem of a right angle triangle. That will always be true. Okay, and so to me, math is another reality check of a truth in itself that I use as a lab to test our theories. And so far, our theories have done brilliantly well to not just corroborate what is known in mathematics, but to also give them new things which, when they check with their own rigorous methods, turns out to be correct. So based on that, I have the academic or intellectual faith that string theory cannot be wrong, and that if something cannot be wrong, can lead us to this thing, then we must seriously contemplate the possibility that this, the fact that we exist as one of the many possible vacuum states is an environmental factor, an environmental phenomenon. Just like why the Moon is this number of kilometers away from the Earth. There's no fundamental reason more than to it. We only know the dynamics of how it goes around, but nothing describes. And I don't think anything can ever describe how far the moon is from the Earth. It just happens during the Big Bang, and then it settles down to be this way. That's it. Yeah. Okay, so that one I think I answered. Okay, so the definition of prediction, okay, has to be relooked in this context. Okay, because we have to relook it as, can anything predict the distance of the Earth and the moon from the moon? We have to predict that. So can anything predict that? I mean, if the answer is no, then this could be the answer to this thing about predictability of the universe of string theory. Okay, so that is the answer. Okay, the final one, I think this one I want to answer also. Okay, are there things that can prove that string theory is wrong? Okay, if there are, why do you believe string theory is still valid? You see, not being able to prove something is wrong doesn't mean it is wrong. Okay, so some people say not even wrong, isn't that? Secretly, people who say that, they admire string theory for the mathematics that it can give out. Okay, Peter Vogt, I know him personally. There's this blog called Not Even Wrong. I spoke to him in person. You know, he's secretly a Witten fan because he loves the mathematics that comes out of string theory. Even he cannot deny that the framework is a body of knowledge, of truth. It's just that people have been, many years people have been trying to say, oh, it's going to give us the theory of the universe and understand everything. And so far for 40 years, people haven't gotten a clue as to how to connect it. That's also because people are rejecting this landscape thing. They're rejecting it. They're saying that fundamental theory still must give you why the universe exists out of 10 to the power 500. I mean, to me, it is, to give an answer to that is the same as saying, the answer why the moon is this far away from us. Okay, if you ask me. Okay, so the thing is, to prove that string theory is wrong, ultimately you must be able to reach experimental energies whereby you can detect the string and then see what it predicts at that level, and then compare and see whether its predictions are correct or not. Okay, but until then, I think it is difficult to prove that it's wrong. But not being able to prove that it's wrong does not mean that it's wrong. Okay, and to me, like I said, in the meantime, since we can't prove it check it against anything, check it against maths. Check it against something that is a Platonic truth. Till the end of time, it is a universal truth on its own. It doesn't matter what you think in biology or chemistry. If a prime number can only be divided by itself, that remains an ultimate truth to the very end. Okay, so that's the nice thing about mathematics. It is in itself an irrefutable, independent truth. My friends who choose to do maths over physics, they say they want to discover things which are eternal truths. Okay, and maths is an eternal truth in itself. Relativity and all that is only true up to 10 to the power minus 10 to the power like 15 decimal places. I think relativity is checked to be accurate up to 15 decimal places. No one can guarantee there will not be a new theory that supersedes relativity as the new theory of mechanics that's more correct than Einstein's theory. Einstein superseded Newtonian mechanics to be correct up to 15 decimal places. Newtonian mechanics was correct up to 12 decimal places, I think. I can't remember, less. Okay, so Einstein's theory is the most accurate theory, but in physics and in science, there will always be something that supersedes it to be more correct. By mathematics, there isn't. So, well, then to me, the best step is therefore maths, because it is in itself another reality check. Nature tells us the truth about itself, nature. But maths tells us a universal truth in itself also. So you want to know whether your theories are right, check it against maths. Okay, so, and then even if you can make predictions for maths, and maths turns out to verify their predictions are correct, then you know you're even more on the right track, because you can make predictions for other truths. Okay, so that's the way I see string theory. All right, got it. Okay, so I guess these two are the other questions which I want to address also, because these are controversial topics, controversial questions that people have, and I've always been dying to answer them. Okay, so yeah, the rest I think maybe you all can write to me. Okay, so they are all kind of standard questions.
Okay, so I think Jianhao can stop the screen share, and all right. I'm sorry for everyone for bearing with us for about 3 hours.
Sorry.
Anyway, it's interesting. So yeah. Anyway, could I invite all of you to turn on your camera for a photo session to commemorate this event? Probably I'll give you 1 minute to get ready. you guys don't mind. And Hong Qian, I think I'll let you, wait a minute. Yeah, Hong Qian, I think I'll let you take over for the photo session. Please be reminded that for USM students, if you don't turn on your cam, then you might not be able to be you might not be awarded for the participation marks because it's been required by the school, by the university. So there we go, we have to bear with it.
Don't be shy, turn on your camera.
All right. Is everyone ready? Yes or no? No, I think not everyone, but I think it's okay. So Hong Qian, I think you can proceed to take the pictures.
Okay, so
Yeah.
now I'm taking for the first page first of 2 pages. So 1, 2, 3. Okay, now I'm taking for the second page. Okay. 1, 2, 3. Okay, done. You may turn off your camera.
All right. I think you guys can proceed to turn off. Okay, so I think that's it for today. Yeah, before you leave, okay, Dini, would you like to share the yeah, okay, she shared the attendance form and also the feedback form. So you guys can fill in until the form will be closed at 5:20. And also if you guys can't manage or don't manage to access through the link, you guys can scan through the screen. And I think that's it for today. Thank you very much. Thank you, Prof Tan, for sharing once again.
Yeah, my pleasure. Thanks for the invitation again. All the best to your studies and everything. Okay.
Yeah, you too, Prof Tan.
All right.
Thank
See you guys.
See you guys
Okay.
around.
Thank you,
Bye.
Professor Tan.
Bye. Thank
Bye.
you.
Thank you, Prof.
Yeah, you're most welcome.